Hello there and welcome to Life Beyond Seen, where the world's quieter mysteries settle in slowly, like sediment drifting down through deep water, patient and unhurried, finding their resting place somewhere in the dark. Tonight we're going somewhere that most people will never see, not because it is hidden behind a fence or locked behind a permit, but because it is hidden behind miles of ocean and thousands of meters of cold, pressurized darkness. Tonight we're going to one of the most powerful and least understood places on this planet, a place that sits just offshore of one of the most densely populated coastlines in South America, and yet remains, in many important ways, almost completely unknown. But let me begin the way this place actually presents itself to the people who live nearest to it. Imagine you are standing somewhere on the coast of Peru, maybe near the city of Lima, where the Pacific stretches out flat and grey in the morning light, the water calm enough to reflect the clouds. Or perhaps further south, along the Chilean coast, where the cliffs drop sharply to the water and the air carries that particular salt and cold smell that ocean air has when it comes from somewhere very deep and very far. From where you stand, the water looks like water. It does the things water does. It moves. It catches light. It carries fishing boats and container ships and the occasional pelican riding a thermal. The horizon sits where it always sits, steady and unremarkable, offering nothing unusual. There is nothing in that view that tells you what is underneath it. Because underneath it, beginning not far from shore and running the entire length of the western coast of South America, is one of the most extreme environments on Earth. A wound in the ocean floor so long and so deep that it genuinely challenges the imagination. This is the Peru-Chile Trench, sometimes called the Atacama Trench, after the desert that runs along the nearby coast. It stretches for approximately 5,900 kilometers, which is longer than the entire width of the continental United States from coast to coast, and at its deepest measured point, it reaches down to around 8,065 meters below the ocean surface. That is more than 8 kilometers straight down, more than 4 times the average depth of the world's oceans, deep enough that if you dropped Mount Rainier into it, the summit would still be well below the waterline. And the thing that makes this trench more than just a very large hole in the seafloor is what is actually happening down there. The Peru-Chile Trench is not a relic. It is not a scar left over from something that finished long ago. It is an active process, running right now, at this moment, in slow motion. The planet is, quite literally, consuming itself along this line. 2 enormous plates of the Earth's crust are meeting here, and one of them is being dragged down into the hot interior of the planet. The trench is the surface expression of that process, the visible crease where the descent begins. Scientists who study this place do not use the word terrifying lightly, but they use it. Or at least they describe things about this trench that make the word feel appropriate. The seismic history alone is enough to justify it. The biological strangeness adds to it. The unresolved questions, the gaps in knowledge about a system that has the power to reshape coastlines and send waves across entire ocean basins, those add to it further. This is a place that has already produced the largest earthquake ever recorded by modern instruments. It sits adjacent to cities where millions of people live, and large sections of it have not broken in centuries. We will get to all of that, slowly, carefully, because it deserves that kind of attention. Before we go any further, I would love to know where you are listening from tonight. Are you somewhere near the ocean, where you can hear it, or at least imagine it just a short drive away? Or are you deep inland, where the nearest coastline is hours of road and open country between you and the water? What time is it where you are? Is it late? The kind of late where the house is quiet and the rest of the world seems to have stepped back a little. I always find that the ocean feels more real in those hours, bigger somehow, more itself. If you enjoy this kind of slow, careful exploration, I would be genuinely grateful if you took a moment to like this video and subscribe to Life Beyond Seen. It is a small thing, but it helps this channel find its way to other people who might need a quiet hour with a fascinating subject. It means a lot. Thank you. Now, back to the water, The Peru-Chile Trench runs along a coastline that is, in many ways, already defined by extremes. To the east, the Andes Mountains rise to some of the highest elevations on the planet. To the west, the trench plunges to some of the lowest points in the ocean. The coastal strip between them is, in places, one of the driest deserts on Earth. The Atacama Desert receives almost no rainfall in some areas, sometimes going years without a measurable drop. And yet offshore, the Pacific supports one of the richest fisheries anywhere in the world. Everything about this region operates at the far end of what is possible, and the trench is, in a sense, the reason for all of it. It is worth pausing here for a moment to let that geography settle in your mind. We are talking about a single connected system. The trench, the mountains, the volcanoes, the desert, the fishery. They are not separate things that happen to share a neighbourhood. They are all consequences of the same underlying process, the same slow collision happening in the crust beneath your feet, or rather, beneath the ocean floor. Understanding the trench means understanding why this entire part of the world looks and behaves the way it does. The alternate name, the Atacama Trench, is used by some scientists and in some publications, though Peru-Chile Trench remains the more common designation in geological literature. Both names point to the same feature, the same extraordinary gash running down the eastern edge of the Pacific Ocean. It does not have the fame of the Mariana Trench, which sits in the western Pacific and holds the record for the deepest point on Earth at around 11,000 metres. The Mariana gets the documentaries, the famous dives, the name recognition. The Peru-Chile Trench is, by comparison, quieter in the public imagination. Which is interesting given that in terms of the direct threat it poses to human populations, it may actually be the more consequential of the two. The Mariana Trench is deep and scientifically remarkable, but it sits far from any major population centres. The Peru-Chile Trench runs alongside a coastline that is home to tens of millions of people. Lima alone, Peru's capital, holds more than 10 million residents. Valparaiso, Iquique, Antofagasta, dozens of cities and towns sit within reach of what this trench can produce, and what it can produce, as history has shown more than once, is catastrophic. But we're getting slightly ahead of the story. Let me bring you back to that image of the water, the ordinary-looking surface, the calm horizon. There is something quietly unsettling about the idea that a feature of this scale exists just out of sight. The trench begins not far offshore. In some places, the seafloor drops away sharply, within a relatively short distance from the coast. From a beach in northern Chile, you are not far, geographically speaking, from the edge of one of the deepest places in the southern hemisphere. The distance between the ordinary world and the extreme world is smaller than it feels. That proximity is part of what makes the trench matter in ways that go beyond pure scientific interest. And the trench is not sitting still. Nothing about this system is static. The plates are moving right now. The stress is accumulating right now. The seafloor is being slowly consumed right now. It has been doing this for tens of millions of years, and will continue doing it long after every city on that coastline has been replaced by something else entirely. On the timescale of geology, human civilization is something that happened very recently and very briefly. The trench predates us by an enormous margin, and will outlast us by the same. That is not meant to be discouraging. It is just the honest framing that the subject deserves. When you're talking about a feature this old and this powerful, it helps to hold it at its actual scale, and its actual scale is humbling. What the trench represents, in the most fundamental sense, is the planet doing what it has always done. Moving, recycling, renewing itself through processes that are violent by human standards, but entirely ordinary by geological ones. The crust that is being pulled down into the mantle along the Peru-Chile Trench will eventually be melted and transformed, its materials return to the surface over millions of years through volcanic activity, through the slow breathing of a planet that has been doing this long before there were eyes to watch it. We are, in a sense, watching a piece of that process. Watching from a distance, from the surface, with our instruments and our expeditions and our questions. The trench does not notice us watching, but we notice it, and the more carefully we look, the more unsettling and the more extraordinary it becomes. The name Atacama Trench carries a certain weight when you say it slowly. Atacama. The word comes from the indigenous Atacameño people of the region, and it carries with it the full strangeness of the landscape it describes. A desert so dry it is used as an analogue for Mars, a coastline so seismically active it has been rebuilt, in places, multiple times within recorded history, and beneath the ocean surface just offshore, a trench that reaches depth that most of the ocean never approaches. This is the place we're going to spend our time with tonight, not rushing through it, not skimming the surface of it, but sitting with it carefully, looking at what it is, what it does, what lives in it, what it has produced, and what it might still produce. Looking at the questions that scientists are still trying to answer about it, and why those questions matter not just academically, but practically, for the millions of people who live in its shadow. The surface of the ocean off the coast of Peru and Chile looks ordinary. The horizon looks calm. But just beneath that surface, the planet is doing something that is anything but ordinary. And the further down you go, the stranger and more consequential it becomes. More. So let us go down, slowly, carefully, starting from the beginning. Starting with the mechanism, the basic geology of what is actually happening beneath the seafloor and why it produces a trench at all. Because to understand why this place unsettles scientists, you first have to understand what it is built from and how it works. The Earth's surface is not one piece. That is easy to say and surprisingly hard to truly absorb. We walk on it, build on it, plant things in it, and it feels so thoroughly solid and permanent that the idea of it being broken into moving sections seems almost theoretical. But it is not theoretical at all. The crust of this planet is divided into large pieces called tectonic plates, and they are in constant slow motion. Not fast enough to watch, not fast enough to feel on any ordinary day, but fast enough, over millions of years, to have rearranged the entire surface of the planet multiple times over. The Peru-Chile Trench exists because two of these plates are meeting at this particular stretch of the Pacific. On one side you have the Nazca Plate, a piece of oceanic crust sitting beneath the eastern Pacific Ocean. On the other side you have the South American Plate, the massive slab of crust that carries the continent of South America. These two plates are moving toward each other. They have been moving toward each other for a very long time. And the trench is what happens at the line where they meet. The Nazca Plate is moving eastward at roughly 7 to 8 centimeters per year. That is about the rate at which your fingernails grow. It sounds trivially slow. But multiply that by millions of years, and you begin to understand the scale of what has happened here. 7 centimeters per year over 10 million years is 700 kilometers of movement. Over 50 million years, it is 3,500 kilometers. The Nazca Plate has been steadily, relentlessly pushing itself towards South America for an enormous span of time, and the consequences of that movement are written across the entire western edge of the continent. When oceanic crust meets continental crust, something has to give, and it is almost always the oceanic crust that loses. Oceanic crust is denser than continental crust. It is made primarily of basalt, a dark, heavy volcanic rock, whereas continental crust is made largely of lighter materials like granite. When these two types of crust collide, the denser oceanic plate tends to bend downward and slide beneath the lighter continental plate. This process is called subduction, and the trench is the surface expression of where that bending begins, the point at which the oceanic plate starts its long descent into the interior of the Earth. Picture the Nazca Plate as a very large, very rigid sheet, being slowly pushed toward a wall. At some point the sheet has to go somewhere. It cannot stack up indefinitely, so it bends. The leading edge tips downward, and the plate begins to angle into the mantle beneath the South American continent. The line where this bending happens, where the plate begins its descent, is where the seafloor drops away sharply and the trench forms. The trench is not a crack exactly. It is more like the outer edge of a curve, the place where the plate flexes before going under. The deepest part of the trench sits right at this flexure point, where the descending plate has pulled the seafloor down with it. The angle at which the Nazca plate descends varies along the length of the trench, and that variation turns out to matter quite a lot. In some sections, particularly beneath central and southern Chile, the plate dives at a relatively steep angle, somewhere around 30 degrees or more. In other sections, particularly beneath central Peru, the plate appears to subduct at a much shallower angle, almost horizontally in places, sliding beneath the continent more like a wedge than a plunging slab. This flat slab subduction, as it is called, has unusual consequences that we will come back to later. But for now, the important thing is simply that the plate is going down, and it is doing so continuously. The Nazca plate is not ancient crust. In geological terms, it is relatively young. The portions of the plate currently being subducted beneath South America are roughly 40 to 50 million years old in many areas, though this varies along the trench. That might sound old by human standards, but for oceanic crust it is on the younger side. The oldest oceanic crust on Earth is around 200 million years old, found in parts of the Western Pacific. The age of the crust matters because it affects its physical properties. Young oceanic crust is warmer, because it has not had as long to cool down since it was formed at a mid-ocean ridge. Warmer crust is slightly more buoyant. It is less dense than old, cold crust that has been sitting on the seafloor for 150 million years and has had time to contract and cool thoroughly. This relative buoyancy of the Nazca plate has real effects on how the subduction behaves. Old, cold, dense oceanic crust tends to sink steeply and readily into the mantle, almost pulling itself down under its own weight. Young, warm, buoyant crust resists sinking more. It takes more force to push it under. This resistance contributes to the locking of the plate interface, the tendency for the two plates to stick together rather than slide smoothly past each other, and that locking is precisely what makes the subduction zone here so seismically dangerous. But again, we will get to that. The mechanism first. As the Nazca plate descends into the mantle, it does not simply disappear. It carries things with it. It carries the oceanic crust itself, obviously, but it also carries the sediment that has accumulated on top of that crust over millions of years, organic material, minerals, and crucially, water. Seawater percolates into the crust through cracks and fissures, and hydrated minerals form within the rock. When the plate goes down and the pressure and temperature increase, these minerals begin to break down and release their water into the surrounding mantle rock above the descending slab. This water does something important. It lowers the melting point of the mantle rock. Rock that would normally stay solid at a given temperature, and pressure can begin to melt when water is introduced. This generates magma, and that magma rises through the overlying crust and eventually erupts at the surface, which is why there is a chain of volcanoes running parallel to the trench, inland from the coast, following the line of the subducting plate. The volcanoes are not a coincidence. They are a direct product of the same process that created the trench. The trench and the volcanic arc are two expressions of one mechanism. The subduction of the Nazca plate beneath South America has been running for something on the order of several tens of millions of years. Over that time, it has not just created a trench and some volcanoes, it has fundamentally shaped the continent. The compression caused by the collision has crumpled and thickened the western edge of South America into the Andes Mountains, the longest continental mountain range on Earth. The Andes stretch for more than 7,000 kilometers from Colombia in the north down to Tierra del Fuego in the south, and they owe their existence to the same collision that carved the trench. The two features are bookends of the same process, the trench where the oceanic plate descends and the mountains where the continental plate has been squeezed and pushed upward in response. The trench goes down, the mountains go up, same engine, and that engine is still running. The Andes are still rising, not quickly by human perception, but measurably. The plate boundary is active, the subduction is ongoing, The mountains are still being built by the same forces that have been at work for millions of years. This is not a fossil system. It is not the remnant of some ancient geological event that has since gone quiet. It is happening now, in real time, at the slow pace of geology, but continuously and without pause. The convergence rate of 7 to 8 centimeters per year does not sound dramatic, but consider what it means for stress accumulation. If the plates are locked together and not sliding freely, that relative motion has to go somewhere. The energy does not disappear. It is stored in the rocks, in the elastic deformation of the crust, building up gradually like a spring being compressed. The longer the plates stay locked, the more energy accumulates, and when they finally unlock, when the stress exceeds the strength of the interface, and the plates suddenly slip, that stored energy is released all at once. That releases an earthquake, and along the Peru-Chile subduction zone, those earthquakes can be of a scale that is genuinely difficult to comprehend. To give you a sense of what 7 to 8 centimeters per year of locked convergence means in practical terms, in a section of the plate boundary that has been locked for, say, 250 years without a major rupture, the accumulated displacement could amount to roughly 17 to 20 meters of potential slip. When that slip happens suddenly, in a matter of seconds or minutes, the ground does not just shake, it lurches. The seafloor moves, the entire coastal region shifts, and the consequences of that kind of movement are enormous. There is something almost strange about the fact that all of this is happening beneath what looks like an ordinary stretch of ocean. Standing on a beach in northern Chile watching the waves come in, you're looking at the surface of a system that extends 8 kilometers straight down and then continues another several hundred kilometers into the mantle beneath your feet. The trench is not visible from the surface. The subducting plate is not visible. The stress accumulation is not visible. None of the mechanism that makes this place so consequential can be seen from where a person stands. You need instruments to detect it, seismometers, and GPS stations and pressure sensors and research vessels. You need data and models and decades of careful measurement. The landscape gives almost no hint of what is going on beneath it, apart from the occasional earthquake, the occasional volcanic eruption, the mountains that are slowly growing to the east. The trench itself, as a physical feature, is the most visible surface expression of all this activity. It is the place where the geometry of the process becomes readable in the shape of the seafloor. Where the plate bends down, the seafloor drops. The trench marks that line. And it is not a small feature. At its deepest measured point, around 8,065 meters, it reaches depths that are genuinely extreme by any measure. The pressure at that depth is approximately 800 times the atmospheric pressure at sea level. The temperature hovers near 2 degrees Celsius. No sunlight reaches anywhere close to that depth. It is a place defined by cold and pressure and absolute darkness, and it runs, this feature, for nearly 6,000 kilometers along the coast. It is not a localized anomaly, it is a continental scale scar. One thing worth holding in mind is that the trench is not uniform along its length. Different sections have different characteristics. The sediment thickness varies. The age and properties of the subducting crust vary. The angle of subduction varies. The degree of locking between the plates varies. The trench is long enough that it crosses multiple geological provinces, and what is true of the trench off northern Chile is not necessarily true of the trench off central Peru. This variability is one of the things that makes it scientifically complex, and also one of the things that makes it difficult to study comprehensively. You cannot characterize the whole system from a single location or a single expedition. The Nazca Plate is being produced at the East Pacific Rise, a mid-ocean ridge in the central Pacific where new oceanic crust is continuously being formed as magma wells up from the mantle and solidifies. The plate moves eastward from that ridge towards South America, and eventually it reaches the trench and begins its descent. The material that makes up the Nazca Plate today was once magma at the East Pacific Rise, perhaps 40 or 50 million years ago. It has been travelling across the Pacific Ocean floor ever since, cooling, accumulating sediment, being slowly colonised by deep-sea organisms, and eventually arriving at the subduction zone to be pulled back into the mantle from which it originally came. It is a complete cycle. Crust is created at the ridge, moves across the ocean floor and is destroyed at the trench. The trench is the destruction end of that cycle. What gets subducted does not come back in the same form. It is transformed by heat and pressure deep in the mantle, and some of its components eventually return to the surface through volcanic activity, but as something entirely different from what went in. This is the basic story of the Peru-Chile Trench at the level of mechanism. A dense oceanic plate moving eastward, meeting a lighter continental plate, bending downward and diving into the mantle at a rate of several centimetres per year. A trench forming at the surface where the plate begins its descent. Stress accumulating where the plates are locked. Volcanoes forming where water released from the sinking plate lowers the mantle's melting point. Mountains rising where the continental crust is being compressed and thickened. It is, in a sense, a beautifully coherent system. Each part connects to every other part. The trench and the Andes and the volcanoes are not separate phenomena. They are one phenomenon seen from different angles. But coherent does not mean gentle. A system this large, running this continuously, accumulating stress at this rate, has produced some of the most powerful earthquakes in recorded history. The same mechanism that built the Andes and carved the trench is also responsible for events that have reshaped coastlines, destroyed cities, and sent waves across the entire Pacific Ocean. The geological process is steady and slow, but its releases are not. They are sudden, enormous, and the consequences of them reach far beyond the immediate region. That history of seismic events, and the ongoing threat of future ones, is where the real weight of this trench begins to make itself felt. So let us follow that connection. Let us trace the same process that carves the trench downward and see what it builds upward, because the two directions are part of the same story, and you cannot really understand one without the other. When the Nazca plate dives beneath the South American plate, it does not simply disappear quietly into the mantle. The collision between these two plates is not just a vertical event, it is also a horizontal one. As the oceanic plate pushes eastward and downward, it presses against the edge of the continent with enormous force. The continental crust, which is thicker and less dense than the oceanic crust, and therefore cannot sink in the same way, has nowhere to go but up. Over millions of years, that upward pressure has produced the Andes Mountains. The same subduction zone that creates the trench on the ocean side creates the mountains on the land side. They are mirror consequences of the same collision. The Andes are the longest continental mountain range on Earth. They run for more than 7,000 kilometers from the southern tip of South America, all the way north through Argentina, Chile, Bolivia, Peru, Ecuador, Colombia, and Venezuela. They contain some of the highest peaks in the Western Hemisphere, including Aconcagua in Argentina, which stands at 6,961 meters above sea level. That makes it the highest mountain outside of Asia, and it owes its existence ultimately to the Nazca plate pressing against the continent from the west. What is worth sitting with for a moment is the scale of that. The trench descends to around 8,065 meters below sea level. Aconcagua rises to nearly 7,000 meters above it. If you could somehow stand at the bottom of the trench and look toward where Aconcagua stands, the vertical difference between those 2 points, measured through the crust and across the continent, is part of the same geological system. The trench and the mountain are connected by the geometry of the plates. The depth of one and the height of the other are both expressions of what subduction does to the material around it. The Andes are also still rising. This is not a process that finished millions of years ago and left a static landscape behind. The subduction is ongoing, the compression is ongoing, and the mountains continue to grow very slowly, at rates that are difficult to detect in a human lifetime, but are real and measurable over geological time. GPS stations placed on Andean peaks have confirmed that the range is still being pushed upward, millimetre by millimetre, year by year. The trench is not a relic of ancient geology. It is an active feature of a living system, and the mountains it is building are still under construction. Now, the compression that builds mountains is not the only thing the subducting plate does as it descends. There is another process happening, one that is perhaps less obvious but equally consequential. As the Nazca plate sinks deeper into the mantle, it carries with it the sediments and seawater that have accumulated on its surface during its long journey across the Pacific. The oceanic crust is hydrated. It contains water locked into its minerals, water in the sediments draped over it, water in the pores of the rock. And as the plate descends and the pressure and temperature increase, that water is squeezed out. It is released from the minerals and driven upward into the overlying mantle wedge, the region of hot mantle rock sitting above the descending plate. This is where the volcanoes come from. Water lowers the melting point of rock. The mantle is already hot enough to be close to melting under normal conditions, and the addition of water from the subducting plate pushes it over the threshold. Pockets of magma form in the mantle wedge, and because magma is less dense than the surrounding rock, it rises. It works its way upward through the crust, accumulating in magma chambers and eventually erupting at the surface. The result is a chain of volcanoes running roughly parallel to the trench, set back from the coast by the distance it takes for the descending plate to reach the right depth to release its water. This chain is called a volcanic arc, and along the Peru-Chile subduction zone it contains dozens of active and potentially active volcanoes. Some of these volcanoes are well known. Villarrica, in southern Chile, is one of the most consistently active volcanoes in South America. It has a permanent lava lake in its crater, which is relatively rare, and it erupts frequently enough that the town of Pucón nearby has had to develop detailed evacuation plans. In 2015, Villarrica produced a significant eruption that sent lava fountaining into the night sky and prompted thousands of residents to evacuate in the early morning hours. It is not a dormant curiosity. It is a working volcano, fed by the same subduction process that is carving the trench several hundred kilometers to the west. El Misti, in southern Peru, is another example. It rises to about 5,822 meters above sea level, and sits directly above the city of Arequipa, Peru's second largest city, which has a population of around 1 million people. El Misti has erupted multiple times in the past few thousand years, and geologists consider it a significant volcanic hazard. The proximity of a large active volcano to a densely populated city is a direct consequence of the subduction geometry. The volcanic arc runs where it runs because of where the plate reaches the right depth. Cities grew where they grew for their own historical and practical reasons. Those two facts do not always align comfortably. Between Villarrica and El Misti there are many others. Sabancaya in Peru has been erupting almost continuously since 2016, sending ash columns several kilometers into the atmosphere on a regular basis. Ubinas, also in Peru, has a history of frequent small eruptions and occasional larger ones. Lascar in Chile is one of the most active volcanoes in the central Andes and has produced explosive eruptions that sent ash across international borders. These are not background features of the landscape. They are active participants in the ongoing geological process, and their activity is directly linked to the subduction happening beneath the trench. What this means, practically, is that the trench, the mountains, and the volcanoes are not three separate things that happen to be located near each other. They are one system. The trench is where the plate descends. The mountains are where the compression from that descent has pushed the continental crust upward. The volcanoes are where the water released from the descending plate has generated magma that rises to the surface. Remove the subduction, and you remove all three. They are expressions of the same process, seen at different points along the same chain of cause and effect. This also means that the people living in Western South America are living inside this system. The cities of Peru and Chile are not located near a geological feature. They are located within it. Lima sits on the coastal plain between the Trench offshore and the Andes rising to the east. Arequipa sits in the shadow of El Misti. Pucón sits next to Villarrica. Santiago sits in a valley flanked by the Andes. These are not abstract geographical facts. They are the daily context of millions of people's lives, most of whom are not thinking about subduction zones while they go about their mornings, but the system does not require their attention to continue operating. There is something worth saying here about the timescale on which all of this operates. The Andes did not rise overnight. The trench did not form in a century. These are processes that have been running for tens of millions of years, and they will continue for tens of millions more. The Nazca Plate has been subducting beneath South America since at least the Mesozoic era, though the current configuration of the subduction zone is somewhat younger. The Andes began their major uplift phase around 25 to 30 million years ago, though parts of the range have older roots. The volcanic arc has shifted position over geological time as the angle and rate of subduction have changed. On these timescales, human civilization is barely a flicker. The entire span of recorded history, from the earliest writing in Mesopotamia to the present day, is roughly 5,000 years. The Andes have been rising for 5,000 times that long. The trench has been forming for even longer. The forces at work here are not on any human schedule. They do not pause between events. They do not accelerate in response to human concern. They simply continue, driven by the heat of the Earth's interior and the physics of plate tectonics, indifferent to everything on the surface. And yet the surface consequences of these slow processes are anything but slow. The stress that accumulates along the plate interface accumulates continuously, but it releases suddenly. The magma that rises through the crust does so over years or decades, but the eruption, when it comes, can happen in hours. The mountains grow by millimeters per year, but the earthquakes that accompany that growth can last for minutes and reshape the landscape in ways that take generations to recover from. The system is slow at the level of mechanism and fast at the level of consequence. That contrast is part of what makes it so difficult for people to hold in mind. The danger is not visible in the daily landscape. It is embedded in the geology, waiting in the accumulated stress of locked faults and the pressurized magma chambers beneath quiet peaks. One thing that scientists have found particularly interesting about the Peru-Chile subduction zone is the way the volcanic arc is not continuous along the entire length of the trench. There are gaps in the arc, sections where volcanoes are absent or much less active than in neighbouring regions. This is not random. It corresponds to sections where the subductic plate appears to be descending at a shallower angle than usual, nearly horizontal in some places, rather than diving steeply into the mantle. In these flat slab regions, the descending plate does not reach the depths where water release and magma generation would normally occur, at least not directly beneath the arc position. The result is a suppression of volcanism at the surface. The volcanoes go quiet or they never form in the first place. Beneath Peru, there is a well-documented flat slab segment where the Nazca Plate appears to subduct at a very low angle for a significant distance before eventually steepening. The reasons for this are still debated, but one factor may be the subduction of thickened oceanic crust, such as the Nazca Ridge, a submarine ridge on the Nazca Plate that is being carried into the subduction zone. Thicker, more buoyant crust resists sinking steeply and may force a shallower angle of descent. Whatever the cause, the flat slab beneath Peru has real surface consequences. It affects the seismicity of the region. It affects the stress distribution in the overlying crust, and it may contribute to the unusual geological character of the central Andes in that region. The trench, in other words, is not a simple feature. It is the surface expression of a process that varies along its length in ways that are still being mapped and understood. The angle of subduction, the age and composition of the subducting crust, the amount of sediment being carried down, the degree of locking between the plates, the presence of submarine ridges or seamounts on the descending plate. All of these variables change from one segment of the trench to the next, and each variable affects the behaviour of the system in ways that matter enormously, when you're trying to assess the hazard that the system poses. What the trench has built, then, is not just a deep canyon on the ocean floor. It has built the longest mountain range on Earth. It has built a chain of active volcanoes that runs through some of the most populated regions of South America. It has shaped the drainage patterns of an entire continent, since the Andes act as a spine that divides rivers flowing west toward the Pacific from rivers flowing east toward the Amazon basin. It has influenced the climate of the continent, since the mountains block moisture-laden air from the Amazon and create the extreme aridity of the Atacama Desert on their western flank. The Atacama, which runs along the coast of northern Chile and southern Peru, is considered the driest non-polar desert on Earth, and its dryness is partly a consequence of the rain shadow created by the Andes, which were built by the subduction that created the trench. All of this from one geological process, one plate diving beneath another. The consequences radiate outward in every direction, shaping landscape, climate, ecology, and human settlement across an entire continent. The trench is the starting point of a chain of effects that reaches from the ocean floor to the highest mountain peaks, to the driest desert, to the densest rainforest on the other side of the range. It is difficult to overstate how central this one geological feature is to the physical character of South America as a whole. But of all the consequences that flow from the trench, the ones that are most immediately felt by the people who live near it are not the mountains or the volcanoes or the desert. They are the earthquakes. The same locking and releasing of stress that is slowly building the Andes is also responsible for some of the largest seismic events in recorded human history. And the history of those events, when you look at it carefully, is genuinely difficult to take in. The 1960 Valdivia earthquake is where you have to start, because there is no other starting point that makes the scale of this place immediately clear. On the 22nd of May, 1960, at 3:11 in the afternoon local time, a section of the plate boundary off the coast of southern Chile ruptured. Not a small section, a section roughly 800 to 1,000 kilometers long and about 200 kilometers wide. The rupture propagated along the interface between the Nazca Plate and the South American Plate, releasing stress that had been accumulating for centuries. The magnitude was 9.5. That is the largest earthquake ever recorded by modern instruments anywhere on Earth. It remains so today, more than 6 decades later. To put a magnitude 9.5 in perspective requires a little patience, because the numbers alone do not communicate the reality. The Richter scale, and more accurately the moment magnitude scale used today, is logarithmic. Each full unit represents roughly 32 times more energy released. A magnitude 9.5 releases approximately 500 times more energy than a magnitude 8.5 and roughly 16,000 times more energy than a magnitude 7.5. The 1960 Valdivia earthquake released more energy than all the earthquakes recorded in the entire second half of the 20th century combined. That is not a rhetorical flourish. Seismologists have actually calculated this. The numbers are real. The earthquake shook southern Chile for approximately 10 minutes. 10 minutes of continuous violent ground motion. Buildings that survived the first minute were subjected to 9 more minutes of shaking. The city of Valdivia was heavily damaged. Landslides blocked rivers. Coastal land subsided by as much as 2 meters in some areas, permanently flooding low-lying regions. The town of Puerto Saavedra was largely destroyed. Estimates of the death toll in Chile range from 1,000 to 6,000, with the uncertainty reflecting the chaos of the disaster and the remoteness of some affected areas. The economic damage was staggering for a country of Chile's size at that time, but the earthquake itself was only the beginning of the event, because the rupture that caused it displaced an enormous section of the seafloor, and that displacement sent energy moving through the entire depth of the Pacific Ocean. The tsunami that followed the 1960 Valdivia earthquake is one of the most documented in history, partly because it travelled so far and affected so many places that records were kept across the entire Pacific basin. The waves reached the coast of Hawaii roughly 15 hours after the earthquake. In Hilo, on the Big Island, the sea withdrew dramatically before the first major wave arrived. People who had gathered on the waterfront to watch were struck. 61 people died in Hawaii. The waves continued westward across the Pacific and reached Japan approximately 22 hours after the initial rupture. In the Sanriku coastal region of Japan, the waves killed 142 people. They also caused damage in the Philippines, in New Zealand, and along the coast of California. The total death toll from the tsunami, across all countries, is estimated at around 1,500 to 2,000 people. The earthquake happened in Chile. People died in Japan. That is the reach of what the Peru-Chile Trench can produce. What makes events like this possible is a mechanism called a megathrust earthquake, and it is worth understanding what that actually means, because the word megathrust gets used a lot without much explanation of the physical process behind it. Along a subduction zone, the two plates are not sliding past each other smoothly. They are locked together along their interface by friction. The descending plate is being dragged downward by its own weight and by the forces of mantle convection, but it is also being held back at the surface by friction with the overriding plate. Over time, this creates an enormous amount of stored elastic energy. The overriding plate is being dragged forward and downward at its leading edge, bending and deforming, while the interior of the continent is being compressed. The strain accumulates over decades, sometimes centuries, sometimes longer. Then, when the frictional resistance is finally overcome, the locked section of the interface breaks free. The overriding plate snaps back, lurching upward and seaward. This sudden, vertical displacement of the seafloor is what generates the tsunami. It is not a small motion. In 1960, the seafloor in some areas moved by several meters in a matter of seconds. The Peru-Chile subduction zone is one of the most seismically active megathrust systems on the planet. The 1960 Valdivia event is the largest, but the history of the region is filled with other enormous earthquakes. In August of 1868, an earthquake estimated at around magnitude 8.5 struck near the city of Arica, which was at that time part of Peru and is now in northern Chile. The earthquake destroyed much of the city and generated a tsunami that swept the harbour clean. 3 warships anchored in the bay were carried inland by the waves. One of them, the USS Wateree, an American gunboat, was deposited about 3 kilometres from the coast and was never refloated. It sat there in the desert for years. The 1868 tsunami travelled across the Pacific and caused damage in Hawaii, New Zealand and Japan, much as the 1960 event would do nearly a century later. In June of 2001, a magnitude 8.4 earthquake struck southern Peru, causing significant damage in the Arequipa region and generating a small but measurable tsunami along the coast. In February of 2010, a magnitude 8.8 earthquake struck offshore south-central Chile, generating a tsunami that killed around 500 people in Chile and sent waves across the Pacific. The 2010 earthquake was the 6th largest ever recorded. In April of 2014, a magnitude 8.2 earthquake struck off the coast of Iquique in northern Chile, generating a tsunami that fortunately caused limited casualties, partly because of improved warning systems and evacuation procedures. These are not rare events spaced out over thousands of years. They are recurring events separated by decades. The plate boundary is generating major earthquakes on a timescale that is very much within human experience. What makes this particularly significant for scientists and for the people who live in the region is the concept of the seismic gap. A seismic gap is a section of a plate boundary that has not produced a major earthquake in a long time relative to its neighbours. The reasoning is straightforward. If the plates are converging continuously, stress is accumulating continuously. A section that has not ruptured recently has been accumulating stress for longer than sections that ruptured more recently. It is, in a sense, overdue. The term does not mean that an earthquake is imminent in any precise way. Earthquake prediction is still far beyond what science can reliably do. but it does mean that the stored energy in that section is likely to be higher than in sections that have recently released their stress. And when it does rupture, the release may be larger. Several segments of the Peru-Chile subduction zone are currently identified as seismic gaps by researchers studying the region. One of the most discussed is the section off the coast of central Peru, near Lima. The last major megathrust rupture in that segment occurred in 1746, an earthquake estimated at somewhere between magnitude 8.6 and 8.8, that devastated Lima and generated a tsunami that essentially destroyed the port of Callao. Lima at that time had a population of perhaps 60,000 people. Today, the Lima metropolitan area has a population of over 10 million. The gap has been accumulating stress for close to 280 years. Researchers who study this segment describe it with a certain careful urgency. They do not say a great earthquake is coming tomorrow, but they do say that this section of the boundary represents one of the most significant unaddressed seismic hazards on the planet. Another gap that has received considerable attention is in northern Chile near the Atacama region. The 2014 Iquique earthquake released some of the stress in that area, but several studies published after the event concluded that the rupture was smaller than the full potential of the gap, and that a significant portion of the accumulated stress remained unreleased. Whether the remaining stress will be released in a series of smaller events or in a single large rupture is not known. That uncertainty is precisely the kind of thing that keeps seismologists working. There is also a broader question about how to measure the degree of locking along different segments of the plate boundary. Scientists use GPS measurements on the land surface to track how the ground is moving, and from those measurements they can infer how tightly the plates are locked together at depth. A highly locked segment is accumulating stress rapidly, and is likely to produce a large earthquake when it breaks. A less locked segment may be slipping more freely, releasing stress in smaller increments. Mapping the locking distribution along the entire length of the Peru-Chile subduction zone is an ongoing scientific effort, and the picture that is emerging is one of considerable variation from one segment to the next. Some areas appear to be very tightly locked. Others show evidence of partial coupling. Still others show signs of what are called slow slip events, episodes of quiet aseismic movement at the plate interface that release stress without generating significant earthquakes. These slow slip events have been detected in several subduction zones around the world and are an active area of research. Their relationship to larger seismic events is not fully understood. Whether they relieve stress in a way that reduces future earthquake risk or whether they can in some circumstances trigger larger ruptures is still being debated. What is not debated is the basic picture. This is one of the most seismically active convergent margins on Earth, with a documented history of producing some of the largest earthquakes ever measured, with multiple identified segments that have not ruptured in a very long time, and with millions of people living close to the source zone. The combination of those three facts is what gives the Peru-Chile Trench its particular place in the concerns of seismologists and disaster risk researchers. It is worth pausing for a moment on what it actually feels like to live with this knowledge if you happen to live in Lima or Iquique or Antofagasta. These are real cities with real daily lives. People go to work, take their children to school, eat lunch, sit in traffic, watch football. The trench is not something most people think about on a Tuesday afternoon, and yet it is there, offshore, invisible, accumulating. The relationship between everyday life and long-term geological hazard is one of the stranger aspects of living in a tectonically active region. The danger is not hypothetical, it is geological fact. But it operates on a timescale that makes it easy to set aside right up until the moment it becomes impossible to set aside. Scientists who study the region are not trying to create alarm. Most of them are careful, measured people who choose their words precisely when speaking about hazard and risk. But when they describe the Lima seismic gap, or the northern Chile situation, or the general state of the plate boundary, there is a particular quality to their language. A kind of careful weight. The kind of language you use when you're trying to communicate something important without causing panic, while also being honest about what the data shows. The data shows that the Peru-Chile Trench has produced the largest earthquake ever recorded. It shows that it has done so repeatedly throughout history. It shows that multiple sections of the boundary are identified as gaps with significant accumulated stress. And it shows that when these sections do rupture, the consequences extend far beyond the immediate coastline, reaching across the Pacific and affecting communities that may not even know the trench exists. Earthquakes this large do not stay contained to the land. The energy moves outward in every direction, and a significant portion of it moves through the ocean, which means that the story of the trench's seismic history is inseparable from the story of the tsunamis it has generated. And those tsunamis, once set in motion, behave in ways that are both physically remarkable and genuinely dangerous to understand. A tsunami is not what most people picture when they first hear the word. The image many of us carry is something from a film, a towering wall of water rushing towards shore visible from miles away, dramatic and dark. The reality is both stranger and, in some ways, more unsettling. In deep water, a tsunami is nearly invisible. It passes beneath ships without being noticed. The wave might be only half a metre tall in the open ocean, but it stretches for hundreds of kilometres from crest to crest, and travels at speeds approaching 800 kilometres per hour, roughly the cruising speed of a commercial aircraft. There is nothing on the surface to warn you, no colour change, no sound, no visible disturbance, just an enormous column of water, the full depth of the ocean, moving quietly in every direction from the point where the seafloor shifted. That shift is what matters. When a megathrust earthquake ruptures along the Peru-Chile Trench, the seafloor does not simply tremble, it moves. The overriding South American plate, which has been locked against the subducting Nazca plate and slowly compressed over decades or centuries, suddenly springs upward. In a major event, the seafloor can be displaced vertically by several meters across a rupture zone that might extend for hundreds of kilometers. That vertical displacement pushes an enormous volume of water upward all at once. The ocean does not absorb this energy, it transmits it. The wave radiates outward in every direction from the rupture zone, moving across the Pacific in concentric arcs, carrying energy that originated at the plate boundary thousands of meters below. The 1960 Valdivia earthquake gives the clearest picture of what this looks like at full scale. When the rupture released on the afternoon of May 22nd, the tsunami it generated was not a regional event, it was a Pacific-wide catastrophe. Waves reached the Chilean coast within minutes, in some places within 15 or 20 minutes of the shaking beginning. The coastal town of Corral was hit by waves estimated at over 10 meters. Other sections of the Chilean coastline experienced waves described by survivors as walls of water arriving in successive pulses, each one pulling debris from the last back into the ocean before the next surge arrived. The pattern of a tsunami is not a single wave. It is a series of waves, sometimes spaced 10 to 30 minutes apart, and the first wave is not always the largest. People who survived the first surge and returned to the coast to assess damage have been killed by the second or third. But the 1960 tsunami did not stop at the Chilean coast. It continued outward across the Pacific, losing height but not energy. Approximately 15 hours after the earthquake, the waves reached Hawaii. In Hilo, on the Big Island, residents had received warnings and many had evacuated. But some returned after what seemed like a modest initial wave, believing the danger had passed. The third wave struck Hilo at around 1 a.m. local time, pushing inland through the downtown area, destroying buildings and killing 61 people. The damage to Hilo was severe enough that entire sections of the waterfront were never rebuilt as residential or commercial areas. Today, that land is a park, a quiet, grassy space along the bay that exists partly because no one wanted to build there again. The waves kept going. 22 hours after the earthquake, they reached Japan. In the Sanriku coastal region, communities that had survived the 1933 Showa Sanriku tsunami were hit again. The 1960 waves killed 142 people in Japan, damaged or destroyed thousands of homes, and caused significant damage to fishing infrastructure. The Philippines also recorded deaths and damage. In total, the 1960 Valdivia tsunami killed somewhere between 1,000 and 2,000 people across multiple countries, the precise figure varying depending on the source and how indirect deaths are counted. It remains one of the deadliest transoceanic tsunamis in recorded history. The 1868 Arica tsunami tells a different kind of story, and in some ways a more locally devastating one. The earthquake that generated it struck on August 13, 1868, in what was then southern Peru. The city of Arica is now part of northern Chile, following the border changes that resulted from the War of the Pacific. The earthquake, estimated at around magnitude 8.5, triggered a tsunami that struck the Arica harbour almost immediately. Several naval vessels anchored in the harbour were carried inland by the waves. The USS Wateree, an American river gunboat, was lifted by the surge and deposited more than a kilometre inland, where it sat stranded in the desert, never returned to the sea. The Peruvian warship America was similarly displaced. The harbour itself was destroyed. The waves from Arica also crossed the Pacific, reaching Hawaii, New Zealand, Japan and Australia, causing damage and deaths along the way. It was one of the events that began to make scientists and naval officers think seriously about the need for some kind of coordinated warning system. That warning system took a long time to arrive. The Pacific Tsunami Warning Center, based in Ewa Beach, Hawaii, was established in 1949, partly in response to the 1946 Aleutian Islands tsunami that had killed 159 people in Hawaii with almost no warning. The 1960 Valdivia event tested the system and revealed its limitations. Warnings were issued, but communication to local authorities and the public was inconsistent, and the decisions people made in those early morning hours in Hilo reflected the difficulty of acting on uncertain information under time pressure. The system has been substantially improved since then, with additional monitoring stations, faster data processing, and better public communication protocols. But the fundamental challenge has not changed. Warning time is finite, and for the communities closest to the source, it is very short. This is where the particular geography of the Peru-Chile Trench creates a problem that no warning system can fully solve. Lima sits roughly 150 kilometers from the trench axis. Iquique in northern Chile is similarly close. Antofagasta is not far behind. These are not small towns. Lima has a population of more than 10 million people. Iquique has around 200,000. Antofagasta has close to 400,000. And when a megathrust earthquake ruptures directly offshore, the tsunami it generates does not need to cross an ocean before it arrives. It is already there. Estimates for wave arrival times at the Lima coastline following a major rupture in the nearby seismic gap range from roughly 15 to 20 minutes. Some models suggest even less, depending on the exact location and character of the rupture. 15 minutes is not a long time. It is enough time to drive a few kilometers in light traffic, or to walk perhaps 1 kilometer on flat ground. Lima's coastal districts, including Miraflores, Barranco and Corrillos, sit at or near sea level along the Pacific coast. The terrain rises steeply in some places, which is helpful. But the density of the population, the number of people who would need to move simultaneously, and the reality that a major earthquake would likely damage roads, knock out traffic signals, and cause widespread panic means that the logistics of evacuation are genuinely difficult. Drills are conducted, evacuation routes are marked. But the gap between a marked route and an actual successful mass evacuation in the minutes following a magnitude 8 or 9 earthquake is a gap that emergency planners think about seriously. Iquique experienced a partial version of this scenario in April 2014. The magnitude 8.2 earthquake that struck offshore that year generated a tsunami that prompted a large-scale evacuation of the city. The waves that arrived were real, up to 2 meters in some coastal areas, and caused damage, though the death toll was relatively low, in part because many residents evacuated quickly, and the earthquake, while large, did not rupture the full extent of the seismic gap. The evacuation itself was described by researchers as imperfect but broadly successful. Traffic jams formed on evacuation routes. Some people moved toward the coast out of curiosity rather than away from it. Communications were disrupted. But most of the population reached higher ground in time. The 2014 event was, in a sense, a rehearsal. Whether it was a rehearsal for something larger that is still to come is one of the questions researchers continue to sit with. The physical behaviour of the tsunami as it approaches shore is worth understanding in some detail, because it explains why the warning time problem is so difficult. In the deep water of the open Pacific, the wave is fast and flat. As it enters shallower coastal waters, it slows down, but the energy it carries does not simply dissipate. Instead, it compresses. The wave height increases. The wavelength shortens. What was a barely perceptible ripple at 5,000 meters depth becomes something entirely different at 20 meters depth. The seafloor topography shapes what happens next. Submarine canyons can focus wave energy, amplifying it in certain locations. Bays can trap and concentrate waves, bouncing them back and forth in a process called resonance that can make later waves larger than the first. The irregular coastline of Peru and Chile means that the tsunami's behaviour varies enormously from one location to the next, and predicting exactly how a wave will behave in a specific harbour or bay requires detailed local modelling. There is also the phenomenon of the drawback, the withdrawal of water from the shore that sometimes precedes the main wave. In some tsunami events, the sea visibly retreats before the surge arrives, exposing the seafloor, stranding fish, revealing rocks and sand that normally submerged. This can happen minutes before the wave arrives. Some people who have witnessed this have understood it as a warning and run. Others throughout history have walked toward the exposed seafloor out of curiosity. The drawback is not a universal feature of all tsunamis, and its absence does not mean a tsunami is not coming. But when it does occur, it is one of the most unambiguous natural warning signs that exists. All of this, the mechanics, the history, the warning times, the evacuation challenges, points toward a single uncomfortable truth about the Peru-Chile Trench and the communities that live near it. The hazard is not theoretical. It is documented, measured, and in some segments, overdue. The Pacific Tsunami Warning System is better than it has ever been. Seismic monitoring networks in Peru and Chile have expanded significantly in recent decades. Public education campaigns exist. Evacuation routes are mapped. And yet the combination of short warning times, dense coastal populations, and the sheer scale of what a major megathrust event can produce means that the risk remains serious and, in certain scenarios, potentially catastrophic. Scientists who study this are not fatalists. They are people who believe that better data, better models, better warning systems, and better public preparedness can reduce harm significantly. Every earthquake that is well studied teaches something useful. Every evacuation drill, however imperfect, builds capacity. Every improvement in seafloor monitoring adds a few more seconds or minutes to the warning chain. These things matter. They have mattered in past events, and they will matter in future ones. But the trench itself is indifferent to all of this, of course. It does not respond to warning systems or evacuation plans or scientific papers. It is simply the surface expression of a geological process that has been running for tens of millions of years, and will continue long after every city on the South American coast has been built, rebuilt, and built again. The energy accumulates, the boundary locks, the stress grows, and somewhere along that 5,900 kilometre scar in the seafloor, in a location and at a time that no model can yet predict with precision, the plate interface will eventually slip. The surface consequences of that process are what make the trench a subject of such sustained scientific attention. But the trench is not only a hazard, it is also a place, a physical environment of extraordinary extremity, sitting at the bottom of the ocean in permanent cold and darkness, largely unexplored, and in some ways more alien than almost anywhere else on the surface of this planet. And what lives down there, in those conditions, turns out to be one of the more surprising things the trench has to offer. So let's go down there for a moment. Not literally, of course. No vehicle carrying a human being has ever reached the deepest point of the Peru-Chile Trench, and for reasons that will become clear, that is not a situation likely to change in the near future. But we can follow the numbers, the measurements, the instrument readings and the sediment samples, and try to build a picture of what that environment actually is. What it feels like in the physical sense. What the conditions are. Because the trench floor is not simply dark water at the bottom of a very deep hole. It is one of the most extreme environments on the surface of this planet, and understanding it changes how you think about the trench as a whole. The depth alone is difficult to hold in the mind. The deepest confirmed measurement in the Peru-Chile Trench is approximately 8,065 meters. That is over 8 kilometers of water column sitting above the floor. To put that in some kind of perspective, if you placed Mount Everest at the bottom of the trench, its summit would still be more than a kilometre underwater. The trench floor is not the deepest point in the ocean. That distinction belongs to the Mariana Trench's Challenger Deep, at around 11,000 metres, but 8,065 metres is still a depth that places the Peru-Chile Trench firmly in what oceanographers call the Hadal Zone. The Hadal Zone is defined as any depth below 6,000 metres, and it is named after Hades, the Greek underworld, which gives you a sense of how scientists have historically felt about it. Below 6,000 metres, conditions shift in ways that make the environment qualitatively different from the deep sea above it. It is not just deeper, it is stranger. At 8,065 metres, the pressure exerted by the water column above is approximately 800 times the atmospheric pressure at sea level. 800 times! The number is technically correct and still somehow hard to fully accept. At that pressure, water behaves differently. Materials that are perfectly solid and rigid at the surface begin to compress in measurable ways. Air spaces collapse. Foam crumbles. Certain metals deform. The human body, which is largely fluid and therefore less compressible than it might seem, would still be destroyed almost instantly at that depth without protection, because the gas-filled spaces, lungs, sinuses, the small air pockets in tissue, would be crushed. Instruments sent to the Hadal Zone must be engineered to withstand this pressure across every component, every seal, every cable junction. A single weak point is enough to lose an entire system. The temperature at the trench floor hovers near 2 degrees Celsius, just above freezing. The water is not frozen because the pressure keeps it liquid, but it is cold in a way that carries its own weight. There is no warmth down there from sunlight, because sunlight does not reach anywhere near the trench floor. The photic zone, the layer of ocean where enough light penetrates for photosynthesis, extends to roughly 200 meters in clear oceanic water. Below that, light fades progressively until, by about 1,000 meters, it is effectively gone. The trench floor at 8,065 meters exists in absolute permanent darkness. Not the darkness of a room with the curtains drawn, or even the darkness of a cave where your eyes eventually adjust. Complete darkness. There is no adjusting. There is nothing to see. The physical structure of the trench itself is worth describing, because it's not simply a flat plane at the bottom of a cliff. The Peru-Chile Trench has the characteristic V-shaped cross-section of most subduction trenches, though the geometry varies along its 5,900 kilometre length. The walls are steep, formed from compressed oceanic crust on one side, and the edge of the South American continental margin on the other. In some sections, the walls are relatively smooth and gradual. In others, they are more abrupt, scarred by landslides, large masses of sediment and rock that have periodically broken away from the trench walls and slid to the floor below. These landslide deposits can be substantial, covering portions of the trench floor with thick accumulations of mixed material. Earthquakes, of which there are many in this region, trigger these slides regularly. The floor itself is covered in sediment. Fine-grained material, clay particles, organic debris, the skeletal remains of microscopic organisms from the water column above accumulate slowly over geological time. But in the Peru-Chile Trench, the sediment story is more interesting than in many other hadal zones because of what is happening at the surface of the ocean directly above it. The Humboldt Current, also called the Peru Current, runs northward along the western coast of South America, and it is one of the most biologically productive ocean currents on Earth. It drives cold, nutrient-rich water up from depth toward the surface in a process called upwelling, and this upwelling feeds enormous blooms of phytoplankton, which in turn supports some of the densest concentrations of marine life in any ocean. The anchovy fisheries of Peru are among the most productive in the world, and they exist because of this current. The seabird colonies on the Peruvian coast, the guano-covered islands that once made Peru one of the world's major fertilizer exporters in the 19th century, exist because of this current. The marine mammals, the fish, the entire coastal ecosystem of Western South America is built on the foundation of what the Humboldt Current delivers, and when all of that life dies, it sinks. Organic material, dead phytoplankton, zooplankton, fecal pellets, fragments of fish tissue, the slow rain of biological debris that oceanographers call marine snow, descends through the water column continuously. In most parts of the deep ocean, much of this material is broken down by bacteria before it reaches the floor. But in areas of high surface productivity like the zone above the Peru-Chile Trench, the flux of organic material is so high that significant quantities reach the bottom even after bacterial decomposition along the way. The trench floor receives an unusually rich input of organic carbon compared to hadal zones in less productive ocean regions. This matters for the sediment. The floor of the Peru-Chile Trench contains more organic material than you might expect from a place that seems so isolated and extreme. Sediment cores taken from the trench show layers of organic rich material interspersed with the more typical fine clays and siliceous ooze. These layers record changes in surface productivity over time. Periods when the Humboldt Current was stronger or weaker, when El Niño events suppressed upwelling, when the overlying ocean was more or less alive. The sediment is, in a sense, a slow record of what was happening at the surface, written in chemistry and particle size in the microscopic remains of organisms that lived and died hundreds of meters above. There are also layers of volcanic ash. The Andes volcanic arc runs parallel to the trench, and eruptions from volcanoes like El Misti in Peru and Villarrica in Chile have periodically sent ash clouds over the Pacific. Some of that ash settles into the ocean and eventually reaches the trench floor. These ash layers are visible in sediment cores as distinct pale bands, and they serve as useful chronological markers. A particular eruption at a known date leaves a signature that helps researchers date the layers above and below it. The physical conditions of the trench, the pressure, the cold, the darkness, the sediment-rich floor, define what kind of life can exist there and how. The hadal zone is not uninhabitable. That used to be the assumption, before the first sampling expeditions reached these depths and found organisms living in conditions that seemed incompatible with life as it was understood. The pressure alone was thought by some early researchers to be a prohibitive barrier. It is not. Life, as it tends to do, found a way. And in the Peru-Chile Trench specifically, the elevated organic input from the Humboldt Current means the trench floor is better supplied with food energy than many comparable hadal environments. The conditions are extreme, but they are not entirely barren. They support a community of organisms that has adapted over evolutionary time to everything the trench can throw at them. What those organisms look like, how they function, and what has been found in their tissues, including some things that were not supposed to be there at all, is where the story of the trench gets genuinely surprising. The Hadal zone has a way of producing findings that researchers did not anticipate, and the biology of the Peru-Chile Trench is no exception to that pattern. Some of what has been collected from these depths raises questions not just about life in extreme environments, but about how far the reach of human industrial activity actually extends. The trench floor, it turns out, is not as isolated from the surface world as its depth and darkness might suggest. The pressure, the cold, the permanent darkness, the organic rich sediment, the V-shaped walls, the slow accumulation of volcanic ash and marine snow, all of it together makes the trench floor a place that is genuinely alien by the standards of surface experience, and yet connected to the surface in ways that are still being mapped and understood. Scientists who study Hadal environments often describe a kind of conceptual shift that happens when you spend time with the data from these places. The trench stops being simply a deep hole and starts being something more like an active participant in the ocean system. It receives material from above, it processes it stores it changes it. The organisms that live there are not passive survivors of an extreme environment. They are functioning parts of a larger system, cycling nutrients, consuming organic material, contributing to the chemistry of the sediment, and in doing so connecting the deepest part of the ocean to processes that extend all the way to the surface. That connection between the extreme conditions at the bottom and the living, productive, sunlit world at the top is part of what makes the Peru-Chile Trench scientifically interesting beyond its geological role. The trench is not just where the plates collide. It is not just where earthquakes begin. It is a habitat, a sediment archive, a chemistry lab operating at pressures no surface instrument can replicate, and a place where the consequences of surface productivity and human industrial activity both arrive, eventually in the dark. Which brings us naturally to the question of what exactly has been found living in those conditions. Because the biology of the Hadal zone, and of this trench in particular, turns out to be one of the more quietly astonishing chapters in the story of life on this planet. The most common animal found in Hadal trenches around the world is also, in many ways, one of the most unexpected. Not some slow, gelatinous creature drifting in the dark. Not a translucent worm barely visible to the naked eye. The dominant fauna of the Hadal zone, including in the Peru-Chile Trench, are amphipods, small crustaceans that look, at first glance, something like tiny shrimp curled into a comma shape. If you've ever turned over a rock in a garden and found those little grey creatures that scatter in all directions, you have met a distant relative of the animals that populate the deepest ocean floors on Earth. The connection is a strange one to sit with, something that familiar, that small-seeming, thriving at 8,000 metres beneath the Pacific. Amphipods in the Hadal zone are not quite the same as their shallow water cousins, though. Depth does something to them. One of the more striking features of Hadal amphipod populations is the phenomenon researchers call gigantism. In many deep-sea environments, organisms tend towards smaller body sizes as food becomes scarce and energy budgets tighten. But in certain Hadal trenches, amphipods actually grow much larger than their relatives in shallower water. Species collected from Hadal depths can reach several centimetres in length, some specimens approaching 10 centimetres or more, compared to the few millimetres typical of many surface water relatives. The explanation is not fully settled, but one leading hypothesis involves cold temperature and the reduced metabolic rate it permits, combined with the relatively high food availability at the trench floor. Slower metabolism, longer lifespan, more time to grow. The Humboldt Current's productivity, which sends so much organic material sinking toward the trench, may be part of why amphipods here have access to enough food to reach those sizes. The species Eurythanes gryllus and related taxa have been collected from the Peru-Chile Trench and studied in some detail. These are scavengers primarily. They are attracted to food falls, the carcasses of fish, marine mammals, or other large organisms that sink to the bottom and represent a sudden, concentrated energy source in an environment where food usually arrives as a slow, diffuse rain of particles. A large food fall on a hadal floor can attract amphipods in enormous numbers within hours. Researchers using baited lander systems, free-falling instrument packages that descend to the trench floor, collect samples or images and then release ballast weights to float back to the surface, have captured footage and specimens showing amphipod aggregations that are genuinely dense. Hundreds of animals converging on a bait package in the dark at 8,000 meters under 800 atmospheres of pressure in water just above freezing. It is not the image most people carry when they think about life in the deep ocean. Beyond amphipods, the trench supports a broader community. Polychaete worms, segmented marine worms with paddle-like appendages, are found in the sediment, burrowing through the organic, rich layers on the trench floor. Some polychaete species have been recovered from hadal depths in multiple trenches and appear to be genuinely adapted to these extreme conditions rather than simply tolerating them. Holothurians, which are sea cucumbers, have also been observed in the Peru Chile Trench. These slow-moving, soft-bodied animals move across the sediment surface, processing sediment for organic material as they go, essentially eating the trench floor and extracting nutrition from it. They can be surprisingly large, and in some hadal environments they represent a significant proportion of the visible megafauna. Foraminifera, single-celled organisms with mineral shells, are present in the sediment in large numbers. They are not dramatic to look at, being microscopic, but they are ecologically important and scientifically valuable. Their shells accumulate in sediment layers and preserve chemical signatures of the water conditions when the organisms were alive. Foraminifera from trench sediment cores have been used to reconstruct past ocean temperatures, oxygen levels, and productivity, contributing to the paleoclimate record that the trench sediment holds. And then there are the microbes, perhaps the most important organisms in the trench in terms of sheer biomass and biogeochemical influence, are the bacteria and archaea living in the sediment. These are piezophilic organisms. The word comes from the Greek for pressure, meaning they are not merely tolerant of high pressure, but actually require it to function optimally. Piezophilic bacteria isolated from hadal sediments have been found to grow poorly or not at all at normal atmospheric pressure. Their cellular machinery, including their membranes and their enzymes, has been modified through evolution to operate under conditions that would disable or destroy the equivalent structures in surface-living microbes. Their membranes contain different lipid compositions that maintain the right fluidity at high pressure and low temperature, where a normal membrane would become too rigid to function. Their enzymes have structural adaptations that keep them flexible and active in conditions that would lock up a standard enzyme like a hinge in cold weather. These microbial communities in the trench sediment are responsible for decomposing much of the organic material that arrives from above. They break down the marine snow, the fecal pellets, the fragments of organisms that have sunk from the sunlit surface. In doing so, they cycle nutrients, releasing nitrogen, phosphorus and carbon compounds back into the water column in forms that can eventually be transported upward and used again by surface organisms. The trench is not a dead end for organic material, it is a processing site. The microbes at the bottom are, in a real sense, part of the same nutrient cycle that supports the Humboldt current's extraordinary productivity at the surface. The connection runs in both directions, from surface to trench floor and back again, mediated by sinking particles and rising water masses. All of this biological activity, the amphipods, the worms, the sea cucumbers, the foraminifera, the microbial mats, exist in conditions that the early pioneers of oceanography would have considered incompatible with life. The pressure alone was thought for a long time to be a hard ceiling. The naturalist Edward Forbes, working in the mid-19th century, proposed what he called the azoic hypothesis, the idea that below a certain depth, perhaps around 500 or 600 meters, the ocean was completely lifeless. The pressure was too great, the cold too severe, the darkness too complete. He was wrong, as subsequent expeditions showed. But the persistence of the azoic idea illustrates how counterintuitive deep sea biology is. The Hadal zone looks from the outside like it should be empty. It is not. What makes the Peru-Chile Trench specifically interesting, beyond the general fact of Hadal life, is the combination of its geological activity and its biological richness. Most Hadal trenches are relatively food-poor environments. The organic material that sinks from the surface is largely consumed by bacteria before it reaches the deepest zones. The trench floor receives a trickle rather than a flow. The Peru-Chile Trench, because of the Humboldt Current, receives something closer to a steady supply. The higher organic input supports a higher biomass of consumers, more amphipods, more worms, more sea cucumbers, than would be expected in a comparable trench in a less productive ocean region. The biology is, in a sense, subsidized by the surface. But the connection between the trench and the surface world carries something else as well. Something that was not discovered until researchers began analysing the tissues of Hadal amphipods in detail and found chemicals there that had no business being at 8,000 metres beneath the Pacific. In research published around 2017, scientists analysing amphipods collected from several deep Pacific trenches, including the Peru-Chile Trench, found high concentrations of persistent organic pollutants in the animal's fatty tissues, specifically polychlorinated biphenyls, known as PCBs, and polybrominated diphenyl ethers, known as PBDEs. These are industrial chemicals. PCBs were widely used in electrical equipment and industrial fluids before being banned in many countries in the 1970s and 1980s, and PBDEs are flame retardants used in plastics, textiles, and electronics. Both classes of chemicals are persistent, meaning they do not break down easily in the environment. Both are hydrophobic, meaning they bind preferentially to fatty tissue rather than water. And both have been found in concentrations that the researchers described as significant, in the bodies of amphipods living in the deepest, most remote parts of the ocean. The mechanism by which they got there is not mysterious exactly, but it is sobering. PCBs and PBDEs released into the environment through industrial discharge, improper disposal, the degradation of old products, enter the ocean, where they bind to particles of organic material. Those particles sink. Slowly, over years and decades, the chemicals migrate downward through the water column, attached to the same marine snow that carries food to the trench floor. When amphipods and other Hadal organisms consume organic material at the bottom, they ingest the chemicals along with the nutrition. Because these compounds accumulate in fatty tissue rather than being metabolized or excreted, they build up over an animal's lifetime. The concentration found in some Hadal amphipods was, according to the researchers involved, higher than levels found in organisms from heavily polluted coastal environments. The deep trench, chemically speaking, was not cleaner than a river running through an industrial zone. It was in some cases worse. This finding landed quietly in the scientific literature, but carried a weight that extended well beyond the question of trench biology. It demonstrated in a very concrete way that the Hadal zone is not isolated from the surface world by its depth. The trench does not exist in a sealed compartment, protected from what happens above it by 8 kilometers of water. The water column is permeable to persistent pollutants. The food web carries them downward. The organisms at the bottom accumulate them. The trench is connected to the surface not just by the organic material that feeds its life, but by the industrial byproducts of human activity that have been entering the ocean for the past century. There is something genuinely unsettling about that finding, and it is worth sitting with for a moment rather than moving past it quickly. The Peru-Chile Trench is one of the most remote environments on Earth. It sits at the bottom of the southeastern Pacific, far from the nearest major industrial centres, accessible only by specialised research vessels operating under difficult conditions, reachable by no human being who has ever lived. And yet, it contains PCBs. The chemicals found in the electrical transformers of mid-20th century factories have made their way, particle by particle, through 8,000 metres of ocean, into the tissues of crustaceans that have never seen sunlight and will never be seen by human eyes without a great deal of technical effort. The trench absorbed what the surface discarded. The implications for understanding deep-sea ecosystems are still being worked through. If hadal amphipods in the Peru-Chile Trench carry these pollutant loads, what does that mean for the organisms that consume them? What does it mean for the microbial communities that decompose their bodies? What does it mean for the sediment record? PCBs and PBDEs in sediment cores could potentially serve as chronological markers in a different way than volcanic ash layers, not marking geological events, but marking the onset and intensity of industrial production in the 20th century. The chemistry of the trench floor carries a human signature now, even at depths that no human has visited. The biology of the trench, taken together, tells a story that is more complicated than the simple narrative of life surviving against impossible odds. Yes, the organisms here are extraordinary. Yes, their adaptations to pressure and cold and darkness are genuinely remarkable. But they are also embedded in a larger system, connected upward to the Humboldt Current, to the surface ocean, to the atmosphere, and, it turns out, to the industrial history of the 20th century. The trench is not a sealed world. It is a receiving end of a very long chain. Scientists who want to understand that chain more fully face a significant practical problem, however. The Peru-Chile Trench is extraordinarily difficult to reach and study. The biology described here has been assembled from a relatively small number of expeditions, a limited collection of samples and observations that are sparse compared to the size and complexity of the environment. The trench runs for nearly 6,000 kilometres. The sampling that has been done represents a tiny fraction of that length and an even tinier fraction of its volume. What has been found is almost certainly not the full picture. The organisms documented so far are the ones that happen to enter a bait trap, or happen to be present in a sediment core taken at a particular location on a particular day. The full biological inventory of the Peru-Chile Trench remains, in honest terms, largely unknown. And reaching the parts that have not yet been sampled is a challenge that the science of deep-sea exploration is still working to meet. That challenge is worth pausing on, because it shapes almost everything about what scientists currently know and do not know about this trench. The Peru-Chile Trench is, in a practical sense, one of the least explored major ocean trenches on Earth. That statement might seem surprising given how significant it is geologically, how seismically active the region is, and how much attention the broader subduction zone has received from earthquake and tsunami researchers over the decades. But geological significance and direct physical exploration are different things. The trench has been studied extensively from the surface, from ships, from satellite data, from seismic instruments on land. Its depths, however, have been visited only rarely and incompletely. The first systematic attempts to measure the trench came from the era of early oceanographic expeditions. The HMS Challenger, which conducted its famous global survey between 1872 and 1876, passed through the eastern Pacific and gathered depth soundings using the technology of its time. A weighted line lowered over the side of the ship, a process that was slow, imprecise, and limited to single-point measurements rather than continuous mapping. The Challenger's contributions to ocean science were genuinely foundational, but the picture it could provide of the trench was rough at best. A few depth numbers, a few bottom samples brought up in trawls, a sense of the general shape of the seafloor in the region. It was a beginning, not an investigation. Later expeditions refined the measurements. The German research vessel Meteor, which conducted Atlantic surveys in the 1920s, and later work in other ocean regions, contributed to improving the bathymetric record of the southeastern Pacific. Mid-20th century oceanographic work, including surveys conducted by American, German, Soviet and Chilean research institutions, began to fill in the depth profile of the trench more systematically. Echo sounding, which replaced the laborious process of wire lowering, allowed ships to measure depth continuously as they sailed, building up track lines of seafloor data. By the latter half of the 20th century, the basic shape of the trench was reasonably well understood, its length, its general depth profile. the location of its deepest measured point at around 8,065 metres. But knowing the shape of something from the outside is very different from knowing what is inside it. The Mariana Trench in the Western Pacific became the reference point for deep-sea exploration, in a way that the Peru-Chile Trench never quite did. Part of this is historical accident. The Mariana Trench's deepest point, the Challenger Deep, became the symbolic target, the deepest place on Earth, the equivalent of Everest for the ocean. In 1960, Jacques Piccard and Don Walsh descended to the bottom of the Challenger Deep in the bathyscaphe Trieste, becoming the first human beings to reach the deepest point of any ocean. That descent, and the subsequent attention it attracted, made the Mariana Trench the primary focus of Hadal research for decades. When James Cameron made his solo dive to the Challenger Deep in 2012, and when the Five Deeps expedition completed its full survey of all 5 ocean trenches between 2018 and 2019, the Mariana remained the prestige target. It has been mapped, sampled, filmed and discussed in a way that the Peru-Chile Trench simply has not. No crewed vessel has ever descended to the deepest measured point of the Peru-Chile Trench. That fact is not widely known, partly because the trench does not have the same cultural profile as the Mariana, and partly because the absence of a crewed descent has not prevented some scientific work from being done. But it is a meaningful absence. A crewed descent, even a brief one, provides something that remote instruments cannot easily replicate. Direct visual observation over a continuous period, the ability to respond in real time to unexpected features, the capacity to collect samples from specific locations based on what the observers actually see, rather than what a pre-programmed instrument happens to encounter. The Trieste descent to the Mariana, limited as it was by the technology of 1960, produced observations that shaped Hadal research for years. The Peru-Chile Trench has not had that moment. What it has had, in more recent decades, is a series of robotic and instrument-based investigations. Remotely operated vehicles, or ROVs, tethered to surface ships by cables that carry power and data, have been deployed in the trench by various research programs. The Schmidt Ocean Institute, a non-profit research organisation that operates the research vessel Falkor, has conducted expeditions in the southeastern Pacific that have included work relevant to the trench and its surrounding region. ROV deployments allow researchers to observe the seafloor in real time via video feeds, collect sediment and biological samples with robotic arms, and measure physical and chemical properties of the water column. They are extraordinarily valuable tools, but they have limitations. The cable tethering an ROV to the surface ship introduces drag and operational constraints. In very deep water, the cable itself becomes a significant engineering challenge. Managing thousands of meters of cable in a moving ship while keeping the vehicle stable and responsive requires careful seamanship and favourable conditions. Operating in the remote southeastern Pacific, far from port facilities and in waters that can be rough, adds logistical complexity to every deployment. Lander systems have become an increasingly important tool for Hadal research, and they have been used in the Peru-Chile Trench with meaningful results. A lander is, in its basic concept, a free-falling instrument package. It is lowered over the side of a ship and sinks under its own weight to the seafloor, carrying cameras, sample traps and sensors. It sits on the bottom for a predetermined period, hours or days, recording video, collecting organisms that enter its bait traps, and measuring local conditions. When the deployment time is complete, it releases its ballast weight and floats back to the surface, where the ship recovers it. The elegance of the lander system is that it does not require a cable connection to the ship during deployment. It operates independently, which means it can reach depths that would be difficult or impossible to manage with a tethered ROV. The biological samples from the Peru-Chile Trench that revealed the PCB contamination were collected using lander systems of this type. The amphipods, the polychaetes, the sediment samples, much of what is known about trench biology comes from these free-falling, self-contained packages rather than from direct observation by human operators. But landers have their own limitations. they sample a small area around their landing point. They attract organisms using bait, which means they are selectively observing animals that are mobile, attracted to food odours, and willing to enter an enclosed space. Sessile organisms, those that live attached to the seafloor, are not captured by bait traps. Rare or sparsely distributed species may not appear at a given landing site, and because lander deployments require ship time, which is expensive, the number of deployments in any given trench is limited. The Peru-Chile Trench stretches for nearly 6,000 kilometres. The number of lander deployments that have been conducted along its length represents a tiny fraction of the possible sampling locations. Researchers are, in a very real sense, drawing conclusions about a vast and varied environment based on a handful of data points scattered along its length. The pressure itself is a constant engineering constraint. At the deepest points of the trench, the pressure is approximately 800 times atmospheric pressure, around 800 bars, or roughly 11,600 pounds per square inch. Every component of every instrument that descends to those depths must be designed to withstand that force without failing. Pressure housings for cameras and electronics must be tested to beyond their rated depths. Syntactic foam, a material made of glass microspheres embedded in resin, is used for buoyancy in deep-sea vehicles because it maintains its volume under extreme pressure in a way that air-filled floats cannot. Batteries must deliver power reliably at near-freezing temperatures under crushing pressure. Connectors and seals must hold against water that is trying, at 800 atmospheres, to find any gap it can. Equipment failures in the Hadal zone are not uncommon, and they are expensive, both in the cost of the lost equipment and in the loss of the ship time that was spent deploying it. Designing for the Hadal zone is a genuinely difficult engineering problem, and the cost of that difficulty is reflected in how infrequently the trench has been directly sampled. There is also the simple question of geography. The Peru-Chile Trench sits in the southeastern Pacific, which is not a region with abundant research infrastructure nearby. Major oceanographic institutions are concentrated in North America, Europe, and Japan. Operating a research vessel in the southeastern Pacific requires either a long transit from distant home ports or logistical partnerships with South American institutions that, while growing in capacity, have historically had fewer resources dedicated to deep-sea research. Peru and Chile both have oceanographic research programs, and Chilean institutions in particular have contributed meaningfully to the study of the Humboldt Current and the broader southeastern Pacific ecosystem. But Hadal research requires specialized vessels and equipment that are expensive to build and operate, and the global fleet of ships capable of conducting serious Hadal science is small. The trench is long, remote, and expensive to reach, and the scientific community has limited resources to allocate across all the questions it wants to answer. What this means in practical terms is that the Peru-Chile Trench, despite being one of the longest and seismically most significant trenches on Earth, remains a place where basic questions are still open. The biological communities at different points along its 6,000-kilometre length have not been systematically compared. The sediment record along most of the trench floor has not been sampled. The water chemistry of the trench interior, the oxygen concentrations, the dissolved organic carbon, the trace metal profiles, is known from a limited number of locations and depths. The physical structure of the trench walls, the frequency and scale of mass wasting events, the distribution of chemosynthetic habitats if any exist, the full range of microbial diversity in the sediments, these are all areas where current knowledge is incomplete. The contrast with the Mariana Trench is instructive, though it is worth being careful about what that contrast means. The Mariana Trench has received more exploration effort in part because of its cultural status as the deepest point on Earth, and in part because of its location in the Western Pacific, closer to the major oceanographic programs of the United States and Japan. It has been mapped more thoroughly, sampled more extensively, and visited by more crewed and uncrewed vehicles than any other trench. Even so, researchers who work on the Mariana regularly note how incomplete the picture remains. How much of its floor has never been directly observed, How many biological and chemical questions are still unanswered? If the Mariana, with all the attention it has received, is still largely unknown, the Peru-Chile Trench is more unknown still. That is not a criticism of the scientists who work on it. It is simply a reflection of the scale of the problem and the limitations of current technology and funding. The trench is there, running at 6,000 kilometers along the edge of South America, doing what it has done for tens of millions of years, receiving the Nazca Plate, accumulating sediment, harbouring life, recording the chemistry of the ocean above it. It does not require human attention to continue being extraordinary. But the gap between its scientific importance and the depth of human knowledge about it is real, and it matters. New tools are beginning to change what is possible. Autonomous underwater vehicles, or AUVs, which navigate without a tether using pre-programmed routes or onboard decision-making systems, can cover larger areas of the seafloor than tethered ROVs, and can operate at hadal depths with appropriately designed pressure housings. Full ocean depth AUVs have been developed and tested in recent years, and their deployment in the Peru-Chile Trench would allow the kind of systematic survey that has never been conducted. Not a single point lander deployment, but a traversal of significant distances along the trench floor, building up a continuous picture of the terrain, the biology, and the chemistry. These vehicles are still expensive and technically demanding, but they represent a genuine advance over what was available a decade ago. The difficulty of exploration, then, is not a permanent condition. It is a current one. The trench that has been sampled only sparsely, visited only by instruments rather than by people, understood only partially despite decades of surface-level study, that trench is at the beginning of a more intensive period of investigation, not at the end of the story. The questions that remain unanswered are not going to stay unanswered indefinitely. They're going to drive research programs, instrument development, and expeditions for years to come. And those unanswered questions, it turns out, are not just interesting scientifically. Some of them are genuinely urgent, because the things that are not yet understood about the Peru-Chile Trench include some of the things that matter most for the safety of the millions of people who live along its coast. So what are those questions exactly? That is worth spending some time on, because the open problems in Peru-Chile Trench science are not vague gestures toward the unknown. They are specific, named, debated puzzles that researchers have been working on for years with incomplete results, and understanding them gives you a much clearer sense of why this particular trench continues to occupy the attention of geophysicists, seismologists, and oceanographers who could, in theory, be working on problems that feel more tractable. The first one is something called flat slab subduction, and it is genuinely strange when you think about what it means physically. In most subduction zones, the descending plate dips downward at a fairly steep angle. Somewhere between 30 and 60 degrees is typical. The Nazca Plate, in most of its length, follows roughly that pattern. But beneath central and northern Peru, something different is happening. There, the Nazca Plate appears to be subducting at an unusually shallow angle, nearly horizontal in some segments, sliding along beneath the South American continent rather than diving steeply into the mantle. In some models, the slab is moving almost flat for hundreds of kilometers before it finally bends downward. This is not a minor geometric detail. The consequences of flat slab subduction are significant and visible at the surface. One of the most noticeable is the suppression of volcanism. In a typical subduction zone, the descending plate reaches depths where pressure and temperature cause the release of water and other volatiles into the overlying mantle wedge. That lowers the melting point of the mantle rock and generates magma, which rises and produces the chain of volcanoes that runs parallel to the trench. That is the system that created Villarrica and El Misti and dozens of other volcanoes along the Andean arc. But in the flat slab segments beneath Peru, the descending plate is too shallow to trigger that process in the normal way. The result is a notable gap in the volcanic arc, a section of the Andes where active volcanoes are largely absent, corresponding to the region above the flat slab. If you look at a map of Andean volcanoes, that gap is visible. It is not a coincidence or a random absence. It is a direct expression of what is happening at depth. What causes the flat slab in the first place is still debated. One widely discussed explanation involves the subduction of buoyant oceanic features, ridges or plateaus on the Nazca Plate that resist sinking and effectively prop the slab up as it descends. The Nazca Ridge, a long underwater volcanic ridge running roughly perpendicular to the trench off central Peru, is often cited as a possible driver. The idea is that as this thicker, more buoyant section of oceanic crust reaches the subduction zone and begins to descend, it resists the downward pull more strongly than ordinary oceanic crust, and the slab flattens out. There is evidence supporting this, but the full picture is not settled. The geometry of the flat slab, how far it extends, how it transitions to normal subduction at its edges, and how it has changed over time are all areas of active research. The flat slab zone also appears to influence seismicity patterns, crustal deformation, and the style of mountain building in the Andes above it, which makes understanding it relevant to questions well beyond pure geophysics. The second major open question involves something called seismic coupling, and it sits right at the heart of the earthquake hazard problem. Seismic coupling refers to how locked the interface between two plates actually is at any given time and place. A fully coupled interface is one where the two plates are effectively stuck together, accumulating elastic strain that will eventually be released as an earthquake. A partially coupled or decoupled interface is one where the plates are sliding past each other more continuously, releasing stress in smaller increments rather than building toward a large sudden rupture. The distinction matters enormously for hazard assessment, because a highly coupled section of the plate boundary is a section that is loading up energy for a future earthquake, while a less coupled section may pose less immediate risk of a major rupture. Measuring seismic coupling along the Peru-Chile subduction zone is technically difficult. It requires dense networks of GPS instruments on land to measure the surface deformation caused by the locked interface, combined with seismic monitoring and modelling. The measurements that exist suggest significant variation along the trench. Some segments appear to be highly coupled, others less so. But the resolution of those measurements is limited, especially offshore, where placing instruments on the seafloor is expensive and logistically demanding. The uncertainty in coupling estimates translates directly into uncertainty in hazard estimates. A section that appears moderately coupled might actually be more locked than the data suggest, or vice versa. Getting this right is not an academic exercise. It is the foundation of understanding where the next large earthquake is most likely to occur and roughly how large it might be. There is also the question of what happens to the sediment that gets carried into the trench and subducted. The Peru-Chile Trench receives a significant supply of sediment from two sources: material transported down the continental slope from the Andes, and organic material sinking from the highly productive surface waters above the Humboldt Current. Some of that sediment accumulates on the trench floor and stays there, but some of it is carried down with the subducting plate, dragged into the mantle in a process called sediment subduction. What happens to it down there is genuinely uncertain. Some of it is probably scraped off and accreted to the base of the overlying plate. Some may be carried deeper into the mantle, where it contributes to the chemical budget of the mantle, and eventually influences the composition of volcanic rocks erupted at the surface. The organic carbon in that sediment is particularly interesting from a climate perspective. Carbon that is subducted into the mantle is effectively removed from the surface carbon cycle for millions of years, while carbon that is returned via volcanism re-enters the atmosphere. The balance between these fluxes, integrated over geological time, influences the long-term carbon dioxide concentration of the atmosphere, and therefore the long-term climate of the planet. The Peru-Chile subduction zone is one of the places where that balance is being set, and the details of how much sediment is subducted versus accreted and how deeply it is carried are not fully known. The fourth puzzle is perhaps the most recently recognised, and in some ways the most counterintuitive. It involves what researchers call slow slip events, or sometimes silent earthquakes. The standard picture of a locked subduction zone is one where stress accumulates steadily and then releases suddenly in a large earthquake. but it has become clear over the past 2 decades or so that the plate interface can also release stress in a much quieter way, through episodes of slow, gradual slip that occur without generating significant seismic waves. These events can involve the movement of centimetres, or even tens of centimetres of slip along the plate interface, which in terms of the energy involved would correspond to a large earthquake. But because the slip happens slowly over days, weeks or months rather than in seconds, it does not radiate the kind of seismic energy that would be felt as shaking. They are detected primarily through GPS measurements of surface deformation, which show the ground moving in ways that are consistent with slip on the plate interface, but are not accompanied by the expected seismic signals. Slow slip events have been documented in several subduction zones around the world, including Cascadia in the Pacific Northwest of North America and various segments of the Japan subduction zone. There is evidence that they also occur along parts of the Peru-Chile subduction zone, though the monitoring networks in the region are less dense than in Cascadia or Japan, which makes detection and characterization more difficult. The significance of slow slip events for hazard assessment is still being worked out. One possibility is that they help relieve stress on the plate interface in a relatively benign way, reducing the energy available for future large earthquakes. Another possibility, which has attracted considerable attention, is that slow slip events can actually trigger large earthquakes by transferring stress to adjacent locked sections of the interface. The 2014 Iquique earthquake in northern Chile was preceded by a period of elevated seismicity and possibly slow slip activity in the region, though the relationship between that precursory activity and the main shock is still being studied. Whether slow slip events are ultimately stress relieving or stress redistributing, and whether either effect dominates in the Peru-Chile context, is an open question with real implications for how the hazard in this region is understood. What ties all of these questions together is that they are not independent puzzles. The flat slab geometry influences where stress accumulates and how it is distributed. The coupling pattern determines where large earthquakes are most likely to originate. The sediment budget affects the mechanical properties of the plate interface, which in turn influences both coupling and the style of slip. Slow slip events interact with the locked sections of the interface in ways that may either buffer or amplify the eventual seismic rupture. These things are all part of one system, and understanding any one of them fully requires understanding how it connects to the others. That kind of integrated understanding is what the current state of research is working toward, and it is not there yet. There is something worth pausing on here, which is that the uncertainty is not a failure of effort or intelligence. The Peru-Chile subduction zone is genuinely one of the most complex tectonic systems on Earth. It spans nearly 6,000 kilometres. It has been active for tens of millions of years. It involves the interaction of 2 major tectonic plates, a continent-scale mountain range, a chain of volcanoes, a deep ocean trench, and one of the most productive ocean current systems on the planet. The geological and geophysical processes operating within it span timescales from seconds, the duration of seismic wave propagation, to hundreds of millions of years, the lifetime of the subducted oceanic crust. Trying to understand all of that from the surface, with instruments that have only existed for a few decades, and monitoring networks that cover only parts of the system, is an enormous undertaking. The open questions are open because they are hard, not because people have not been paying attention. And yet, the urgency of answering them is real, because sitting above this system, on the coastal plain between the Andes and the Pacific, are millions of people, in Lima and Callao, in Iquique and Antofagasta, in dozens of smaller cities and towns that have grown up along the coast of Peru and Chile over centuries. They live within the reach of whatever the trench decides to do next. The scientific questions about flat slab geometry and seismic coupling and sediment subduction and slow slip are not abstract. They are the questions that determine how well those cities can be prepared for what is coming. And what is coming, in broad terms, is not in doubt. The only question is when and how large, and whether the systems designed to protect people will be ready in time. That question, what a future major rupture along this trench could actually look like and what is genuinely at risk, is where the story leads next. So let us think about Lima for a moment. It is a city of more than 10 million people spread across a long coastal plain between the Andes and the Pacific. It is one of the largest cities in South America, one of the largest in the Western Hemisphere. It has neighbourhoods that stretch from the cliffs above the ocean all the way inland toward the foothills. It has a dense, layered urban fabric that has been building up for centuries on top of ground that in many places is sandy alluvial fill, soft sediment deposited by rivers coming down from the mountains, the kind of ground that does not behave well when it shakes. And it sits almost directly above one of the most dangerous seismic gaps in the world. The last time a truly major megathrust earthquake ruptured the section of the plate boundary closest to Lima was in 1746. That event is estimated to have had a magnitude somewhere between 8.6 and 8.8, which puts it in the same general category as the 2010 Chile earthquake, and not far below the 1960 Valdivia event. The ground shaking in Lima during the 1746 earthquake was severe enough to destroy most of the city's buildings, which at that time were primarily adobe and masonry construction. But the shaking was not the only danger. A tsunami followed. It struck the port of Callao, which sits at the edge of Lima's coastal plain, and the destruction there was nearly total. Contemporary accounts describe the harbour being swept clean. Ships were carried inland. Structures that had survived the shaking were taken by the water. The death toll in Callao alone was in the thousands, out of a population that was far smaller than it is today. That was roughly 280 years ago. In the intervening time, the section of the plate boundary responsible for that event has not produced a comparable rupture. The Nazca Plate has continued moving eastward at its steady rate of around 7 to 8 centimetres per year. The interface between the two plates in this segment has remained largely locked, accumulating stress with every passing decade. The elastic strain energy being stored in the crust around Lima has been building for nearly 3 centuries, and the question of when it will be released is one that Peruvian and international seismologists think about with considerable seriousness. To put some numbers around what that accumulated stress represents, if the plates have been locked and converging at roughly 7 centimetres per year for 280 years, that is approximately 20 metres of potential slip that has not yet happened. Not all of that will necessarily be released in a single event. Subduction zones are complicated, and stress can be distributed across multiple ruptures or partially released in smaller earthquakes. But the broad picture is one of a system that is significantly overdue by any reasonable accounting. Scientists are careful not to say that an earthquake is imminent, because the timing of large earthquakes remains genuinely unpredictable. But they are equally careful not to say that the hazard is remote or uncertain. It is neither. It is specific, it is well documented, and it is serious. What would a repeat of 1746 actually look like in the Lima of today? That is a question that researchers and civil engineers have been trying to answer in increasingly detailed terms. The ground shaking itself would be severe and prolonged. A magnitude 8.7 or larger megathrust event on this segment of the subduction zone would generate shaking that could last several minutes. Not the 10 or 15 seconds of a typical moderate earthquake, but something much longer and more exhausting to structures. The duration matters enormously for building damage, because even structures that might survive a short, sharp pulse of shaking can be progressively weakened and eventually fail if the motion continues for 2 or 3 minutes. Lima has a significant stock of older buildings that are vulnerable to this kind of sustained shaking. Adobe construction, which was common in earlier centuries and is still found in older neighbourhoods and in poorer districts, performs very poorly in earthquakes. It is heavy, brittle, and tends to collapse rather than flex. Unreinforced masonry, brick or concrete block without steel reinforcement, behaves similarly. There have been major efforts in Peru to assess and retrofit vulnerable buildings and Lima has modern construction standards that require earthquake-resistant design for new structures. But the city has grown so large and so quickly that the inventory of potentially vulnerable buildings remains enormous. A detailed seismic risk assessment published in the years following the 2007 Pisco earthquake, which struck southern Peru at magnitude 8.0 and caused widespread damage, estimated that tens of thousands of buildings in Lima would be at significant risk in a larger event. The soft sediment issue compounds this. In earthquake engineering, there is a well-understood phenomenon called site amplification, where seismic waves travelling through soft, unconsolidated ground are amplified compared to what would be experienced on hard rock. The soft alluvial deposits that underlie much of Lima's coastal plain and river valleys would amplify ground shaking significantly in a major earthquake. Some areas could experience shaking several times more intense than what would occur on bedrock nearby. And in certain conditions, particularly in areas with a high water table and loose sandy soil, there is the additional hazard of liquefaction, where the ground temporarily behaves more like a liquid than a solid, causing buildings to sink, tilt, or collapse, even if they were structurally capable of withstanding normal ground motion. Then there is Callao and the tsunami. Callao is Lima's port district, sitting directly on the coast. It is a densely populated area with industrial facilities, residential neighbourhoods, and infrastructure that serves the entire metropolitan region. The port itself is one of the busiest on the South American Pacific coast. In a megathrust rupture on the Lima segment, the seafloor displacement would generate a tsunami that would begin moving towards shore almost immediately. The distance from the trench to the coast at Callao is roughly 100 to 150 kilometres. At typical tsunami propagation speeds in the deep water of the trench, that distance translates to a travel time that some models estimate at around 15 to 20 minutes before the first wave arrives at the shore. 15 to 20 minutes sounds like enough time. In practice, it is not much. A tsunami warning requires that the earthquake be detected and characterized, that the detection trigger an alert, that the alert be transmitted to emergency management authorities, that those authorities activate sirens and broadcast systems, and that the population understand what the warning means and begin moving to higher ground. Each of those steps takes time. The earthquake detection and initial characterization by seismic networks can happen within a few minutes of the event, but the subsequent steps eat into the remaining window quickly. And in a scenario where the earthquake itself has just caused severe shaking, communications infrastructure may be disrupted, roads may be blocked by debris or cracked pavement, and people may be disoriented or injured. Moving tens of thousands of people from low-lying coastal areas to safe elevations in 15 minutes under those conditions is an enormous challenge. Peru has invested in tsunami warning infrastructure and public education, and there are designated evacuation routes and assembly points in coastal areas. After the 2004 Indian Ocean tsunami, which killed over 220,000 people across multiple countries and prompted a global reassessment of tsunami preparedness, many Pacific nations, including Peru, significantly upgraded their warning systems and public awareness programs. The Pacific Tsunami Warning Center in Hawaii, which was established partly in response to the 1960 Valdivia tsunami, plays a central role in detecting and disseminating tsunami warnings across the Pacific Basin. But there is an inherent limitation for near-source events like a Lima rupture, which is that the warning time is simply very short compared to what is needed to evacuate large numbers of people from a densely populated coastal city. The 2014 Iquique earthquake in northern Chile provides a useful, if sobering, reference point. That event had a magnitude of 8.2 and occurred on the northern Chile subduction zone, a section of the plate boundary that had also been identified as a seismic gap. The earthquake generated a tsunami, and evacuations were carried out in Iquique and nearby coastal towns. The response was generally considered to have gone reasonably well. There were casualties, but the death toll was limited in part because the warning systems functioned, and the population had been educated about what to do. but many researchers noted that the 8.2 event, while large, may not have fully released the stress in the northern Chile Gap. Some analyses suggested that the rupture area was smaller than the full extent of the locked zone, and that a larger event on the same or adjacent segment remained possible. That pattern, a significant earthquake that provides some relief but does not fully resolve the underlying hazard, is one that makes seismic hazard assessment particularly difficult. The 2010 Chile earthquake of magnitude 8.8, which ruptured a long segment of the central Chile subduction zone and generated a major tsunami, was in some ways a partial analogue for what could happen in the Lima segment. The 2010 event caused widespread damage in central Chile, triggered a Pacific-wide tsunami warning, and killed over 500 people despite relatively good warning systems and a population with considerable earthquake experience. Scaling that scenario to the Lima metropolitan area, with its larger population, greater building vulnerability, and more complex evacuation geography, gives a sense of the potential consequences. It is worth being careful here about the difference between what is known and what is projected. Scientists know that the Lima seismic gap is real, that it has been accumulating stress for a long time, and that a major rupture is expected at some point. They do not know when that rupture will occur. They do not know exactly how large it will be, how long the rupture zone will extend, or precisely how the slip will be distributed along the fault. The models of ground shaking, tsunami generation, and building damage are probabilistic. They describe ranges of possible outcomes, not single predictions. The uncertainty in those models is real, and researchers are honest about it. What the models do agree on, broadly, is that the potential for a catastrophic event in the Lima region is among the highest of any major urban area in the world. A 2015 study published in the journal Earth and Planetary Science Letters, examining the seismic history and coupling of the central Peru subduction zone, concluded that the Lima segment represents one of the most significant unruptured seismic gaps on the planet. Other assessments have reached similar conclusions. The combination of a long recurrence interval, a large locked area, a densely populated coastal zone with significant building vulnerability, and a short tsunami warning time makes this one of the scenarios that disaster risk researchers return to repeatedly. Early warning systems are one piece of the response. Peru operates a seismic early warning system, and there are ongoing efforts to expand its coverage and reduce the time between earthquake detection and alert issuance. The goal of earthquake early warning is slightly different from tsunami warning. It aims to provide a few seconds to perhaps a minute of warning before strong shaking arrives at a given location, which is enough time for people to take protective action, like dropping to the floor and covering their heads, or for automated systems to stop trains, open fire station doors, or shut off gas valves. Japan's earthquake early warning system, which is among the most sophisticated in the world, provides a useful model, though Japan has had decades and significant resources to build out its network. Peru's system is less mature, and the warning times achievable for a near-source Lima event would be very short. The deeper limitation, which engineers and emergency managers acknowledge, is that early warning and evacuation planning can reduce casualties, but cannot eliminate them in a scenario of this magnitude. The most effective long-term risk reduction is mitigation, building structures that can withstand strong shaking, retrofitting vulnerable buildings before an event, ensuring that critical infrastructure like hospitals, bridges and water systems can survive a major earthquake, and planning land use so that the most vulnerable populations are not concentrated in the most hazardous areas. These are slow, expensive, difficult processes, particularly in a city as large and economically diverse as Lima. Progress has been made, but the gap between the current state of the built environment and what would be needed to significantly reduce casualties in a major event remains large. There is something quietly sobering about sitting with all of this. The trench is there, offshore, running along the coast, doing what it has always done. The plates are moving, the stress is accumulating, the cities are growing, the science is improving, And somewhere in the gap between what is known and what can be done lies the real challenge. Not just understanding the hazard, but translating that understanding into action fast enough and thoroughly enough to make a difference when the moment comes. That challenge is not unique to Lima or to Peru and Chile. It is the fundamental challenge of living near a subduction zone. But the scale of what the Peru-Chile Trench represents, in terms of both the energy stored in its locked interface and the number of people living within its reach, makes it one of the most pressing versions of that challenge anywhere on Earth. Understanding that hazard more fully, and preparing for it more effectively, requires understanding the trench itself, in ways that current technology still struggles to achieve. And that brings us to something that might seem distant from earthquake engineering but turns out to be deeply connected: the surface ocean system that the trench has helped to shape, and that in turn shapes the trench in ways that are only beginning to be understood. The surface of the Pacific Ocean off the coast of Peru looks, on most days, like any other stretch of open water: blue-grey, windswept, moving in long, slow swells. There is nothing visible to suggest that the water here behaves differently from the ocean 1,000 kilometers to the west. But it does. The Peru-Chile Trench, running along the seafloor beneath, is not just a geological feature. It is part of a larger physical system, and one of the most consequential expressions of that system flows along the surface in the form of a current that has shaped the ecology, the economy, and the climate of an entire coastline for millions of years. The Humboldt Current, also known as the Peru Current, is one of the great ocean currents of the world. It moves northward along the western coast of South America, carrying cold, deep water up from the south and drawing it toward the equator. The current is driven partly by wind patterns. The southeast trade winds push surface water away from the coast, and cold water rises from below to replace it. This process, called upwelling, is what makes the Humboldt Current so extraordinary. Deep ocean water is rich in dissolved nutrients, nitrates, phosphates, silicates, that have accumulated over long periods as organic material sinks from the surface and breaks down in the depths. When that nutrient-rich water rises to the sunlit surface zone, it fuels explosive growth of phytoplankton, which feeds zooplankton, which feeds fish, which feeds seabirds and marine mammals, and eventually people. The result is one of the most biologically productive ocean systems on Earth. The anchovy fishery off the Peruvian coast has historically been among the largest single-species fisheries in the world by volume. In good years, Peruvian fishing fleets have landed 8, 9, even 12 million metric tons of anchovies in a single year. Those numbers are almost abstract until you try to picture them. 12 million metric tons is roughly the combined weight of every person currently living in Lima, multiplied several times over. The anchovies feed not just the fishing industry, but the broader marine food web. The Humboldt penguins, the Peruvian pelicans, the guanay cormorants that nest in enormous colonies on offshore islands and have, over centuries, deposited guano layers thick enough to be mined commercially as fertilizer. The entire system runs on upwelling, and upwelling runs on the interaction between wind, water, and the shape of the coast. The trench is part of that shape. The steep underwater topography along the Peru-Chile margin, the narrow continental shelf, the abrupt drop into deep water, all of these influence how and where upwelling occurs, how currents move along the coast, and how efficiently nutrients are recycled through the system. The trench is not a passive bystander to the Humboldt Current. It is part of the physical structure that the current moves against and along. And what goes down into the trench is in large part a product of what the current produces at the surface. The Humboldt Current drives such high biological productivity in the overlying water that an unusually large amount of organic material, dead phytoplankton, fecal pellets, the remains of larger organisms, sinks continuously through the water column and eventually reaches the seafloor. Some of it accumulates on the continental shelf, some drifts farther and settles into the trench itself. This is why the Peru-Chile Trench has a richer organic sediment layer than many other hadal environments. The biology of the surface is literally raining down into the darkness below, and the organisms that live in the trench, the amphipods, the polychaete worms, the sea cucumbers, the microbial communities, depend on that rain of organic material as their primary food source. The trench's biology and the surface ocean's biology are not separate systems. They are one connected flow, from sunlight to phytoplankton to fish to sediment to Hadal seafloor. That connection becomes dramatically visible when El Niño arrives. El Niño is a periodic climate pattern originating in the tropical Pacific, in which the normal westward flow of warm surface water across the equatorial Pacific weakens or reverses. Warm water that is usually pushed toward Indonesia and Australia instead piles up along the western coast of South America. When that happens, the thermocline, the layer separating warm surface water from cold deep water, deepens. The cold, nutrient-rich water that normally upwells along the Peruvian coast can no longer reach the surface. The upwelling is suppressed. The cold, Humboldt current weakens. The sea surface temperature along the Peruvian coast rises by several degrees, and the entire biological system that depends on upwelling begins to collapse. The consequences are not subtle. During a strong El Niño, anchovy populations crash because the phytoplankton they depend on disappears. The seabirds that eat the anchovies abandon their nesting colonies or starve. Marine mammals suffer. The fishing industry, which is a central part of Peru's economy, takes severe losses. The El Niño of 1972 to 1973 was one of the worst on record at that time. Anchovy catches, which had reached around 12 million metric tons in 1970, fell to less than 2 million metric tons by 1973. The collapse was so severe that it contributed to a global protein crisis. Peruvian fish meal was a major input for livestock feed in Europe and North America, and its sudden scarcity drove up the price of soybeans and other feed alternatives worldwide. The ripple effects of what happened in one stretch of Pacific Ocean were felt in supermarkets on the other side of the planet. The 1997 to 1998 El Niño was stronger still, by some measures the most powerful El Niño of the 20th century. Sea surface temperatures along the Peruvian coast rose by as much as 4 or 5 degrees Celsius above normal. The fishery collapsed again. Flooding struck coastal Peru, while drought hit other parts of South America and beyond. The event caused an estimated $33 billion in economic damage globally. It reshaped weather patterns across the Americas, Australia, Africa, and Asia. And at the seafloor of the Chile Trench, the input of organic material from the surface changed dramatically. The biological pulse that normally feeds the Hadal community was interrupted. What this means for the organisms living in the trench during an El Niño event is not fully understood. The trench is deep enough that changes in sea surface temperature do not directly affect it. The water at 8,000 meters stays near 2 degrees Celsius, regardless of what the surface is doing. But the food supply changes. The rain of organic material from above diminishes when surface productivity collapses. How quickly that reduction propagates to Hadal depths, how long it persists, and how the trench community responds are questions that researchers are still working to answer, partly because the trench is so difficult to monitor continuously over the timescales needed to capture El Niño cycles. There is also the question of what El Niño events leave behind in the sediment record. The layered sediments on the floor of the Chile Trench are not uniform. They preserve variations in the organic material deposited over time, richer layers corresponding to periods of high productivity, thinner or chemically different layers corresponding to El Niño events when productivity was suppressed. Researchers who analyze sediment cores from the trench can, in principle, read those layers like a slow diary, identifying past El Niño events, estimating their intensity, and building a record that extends back thousands of years before any human observer was present to document them. This kind of paleoclimate record is genuinely valuable. Instrumental records of El Niño go back only about a century and a half in any reliable form. Sediment cores from the trench can potentially extend that record by orders of magnitude, giving climate scientists a much longer baseline for understanding the natural variability of the El Niño system and how it may be changing. It is one of those instances where a place that seems purely geological turns out to carry biological and climatic history inside it, layer by layer, pressed into the sediment under the weight of everything above. The connection between the Humboldt Current and the trench also runs in the other direction, from the deep toward the surface, in ways that are less obvious but no less real. The trench and the broader subduction margin influence the shape of the seafloor and the continental shelf, which in turn affects where and how strongly upwelling occurs. The narrow shelf along the Peruvian coast, a direct consequence of the tectonic setting that created the trench, means that cold water rising from depth does not have far to travel before it reaches the coastal zone where phytoplankton can use it. A wider, shallower shelf would diffuse the upwelling differently. The mountains onshore, built by the same subduction process that created the trench, shape the wind patterns that drive upwelling in the first place. The whole system, trench, margin, shelf, mountains, winds, current, fishery, is one interconnected structure assembled over tens of millions of years by the slow collision of two plates. It is worth pausing on that for a moment. The fact that Peru is one of the world's major fishing nations, the fact that enormous seabird colonies exist on islands off its coast, the fact that the cold waters there support a marine ecosystem of remarkable richness. None of these things are accidents of geography in any simple sense. They are downstream consequences of the Nazca Plate diving beneath South America. The trench is not just a hazard to be feared or a scientific puzzle to be solved. It is the reason the coastline looks the way it does, the reason the ocean there behaves the way it does, and the reason that millions of people have been able to build livelihoods around the sea for thousands of years. That is a strange kind of thing to sit with. The idea that one of the most biologically generous ocean systems on the planet exists because the same geological process that makes the ground shake and the ocean surge has also, over a very long time, arranged the physical world in a way that concentrates nutrients and life in one place. The trench gives and takes in ways that are not neatly separated. For the scientists who study the Humboldt Current and the Peru-Chile Trench together, one of the active research questions is how the balance between these systems might shift as the climate continues to change. Warmer ocean temperatures, changes in wind patterns, and shifts in the behaviour of the El Niño cycle could all affect upwelling intensity and frequency. Some models suggest that climate change may alter the strength or location of upwelling zones, with consequences for fishery productivity that are difficult to predict precisely. Whether the trench's sediment record can help constrain those projections by providing a longer baseline of natural variability is something researchers are actively exploring. What makes all of this more than just an interesting ecological story is that it connects directly to the same deep ocean processes that govern carbon cycling, ocean chemistry, and the long-term regulation of Earth's climate. The Humboldt Current's productivity, the organic material it sends sinking into the trench, the subduction of carbon-bearing sediments into the mantle, these are not separate threads. They are part of one planetary system, and understanding how they interact is part of understanding how the Earth manages its own chemistry over geological time. That dimension of the story, the trench as a node in the planet's carbon cycle, opens into a set of questions that are, in their own way, just as profound as the earthquake hazard and just as incompletely answered. So let us follow that thread a little further, because the carbon story is one that tends to get overshadowed by the more immediately dramatic aspects of the trench, the earthquakes, the tsunamis, the strange biology. But it may be, in the very longest view, one of the most consequential things the Peru-Chile Trench does. The Earth has a carbon cycle, and most people are familiar with the short version of it. Plants absorb carbon dioxide, animals breathe it out, oceans exchange gases with the atmosphere, and so on. That cycle operates on timescales of years to centuries, and it is the one that gets discussed most often in the context of climate change. But there is a longer version of the carbon cycle, one that operates on timescales of millions of years, and subduction zones like the Peru Chile Trench are among its most important components. Here is roughly how it works. Carbon enters the ocean in various forms, dissolved in seawater, incorporated into the bodies of marine organisms, carried in sediment washed off the continents. When those organisms die, their remains sink. Some of that organic material is decomposed in the water column before it reaches the bottom. Some of it makes it all the way down to the seafloor, where it accumulates in sediment. Over time, sediment layers build up, compress, and harden. And at a subduction zone, some of that sediment, along with the oceanic crust beneath it, gets carried down into the mantle. What happens to the carbon at that point is not a simple story. Some of it is released relatively quickly, geologically speaking, when the subducting slab heats up and releases fluids. Those fluids rise into the overlying mantle wedge and can eventually make their way back to the surface through volcanic activity. The chain of volcanoes running along the Andes, El Misti, Villarrica, and the dozens of others in the volcanic arc, are, among other things, outlets for material that was once on or near the sea floor. Carbon dioxide emitted by Andean volcanoes includes carbon that was subducted at the trench. It is a slow loop, taking millions of years to complete, but it is a real one. Some carbon, though, goes deeper. It gets carried into the mantle proper and stored there on timescales that are difficult to even conceptualize, hundreds of millions of years potentially. The fate of subducted carbon at great depth is an active area of research, and scientists are still working out what proportion gets returned to the surface relatively quickly through volcanism versus what proportion gets sequestered in the deep mantle for geological epochs. The answer matters because it affects how the long-term carbon cycle has regulated Earth's climate over hundreds of millions of years, keeping the planet within a range that has allowed liquid water and life to persist. The Peru Chile Trench is one of the places where researchers are trying to get better constraints on these numbers. The Humboldt Current makes this trench an interesting case study because, as discussed, it delivers unusually large amounts of organic carbon to the trench floor. The trench is, in this sense, a particularly active node in the carbon burial system. Organic material from one of the ocean's most productive surface ecosystems is being funneled down to hadal depths and eventually into the subduction zone. How much of that carbon ends up buried in trench sediments, how much gets subducted into the mantle, and how much is remineralized by microbial communities on the trench floor are questions that researchers are working to quantify. This is not purely abstract science. The long-term carbon cycle is one of the mechanisms by which the Earth has maintained a habitable climate across billions of years, and understanding how efficiently subduction zones sequester carbon versus return it to the surface is part of understanding how that regulatory system works. If the Peru Chile Trench is subducting a large amount of organic carbon and delivering a meaningful fraction of it to the deep mantle, that represents a carbon sink operating on geological timescales, one that does not show up in short-term carbon budgets, but matters enormously over the longer view. There is also a more immediate dimension to the carbon story. The organic sediments accumulating on the trench floor right now represent a form of carbon sequestration that is happening on human timescales. The Humboldt Current drives high surface productivity. Organisms die and sink, and their carbon-rich remains accumulate in the trench at rates that are relatively high for a hadal environment. Researchers studying the trench's sediment chemistry have found that the organic carbon content of the sediments is notably elevated compared to other deep-sea trenches that lack an equivalent surface current. This makes the Peru Chile Trench an interesting natural experiment in how ocean productivity and deep-sea carbon burial are connected. Sediment cores extracted from the trench floor carry all of this history in their layers. A sediment core is exactly what it sounds like, a cylinder of sediment extracted from the sea floor. typically by a gravity corer or a piston corer that is lowered from a research ship and driven into the sediment by its own weight. The core captures layers of sediment in sequence, with the oldest material at the bottom and the most recent at the top. Analysing those layers, their chemical composition, their organic content, the microscopic fossils they contain, the isotopic ratios of carbon and oxygen locked inside them, allows researchers to reconstruct a history of conditions in the water column, above and on the seafloor itself. In the Peru Chile Trench, sediment cores have revealed several kinds of records layered on top of one another. There are the variations in organic carbon content that reflect past changes in Humboldt current productivity, including the signatures of El Niño events. There are records of changing oxygen levels in the water column, which affect how much organic material survives the journey to the bottom. There are microscopic organisms called foraminifera, tiny single-celled creatures with calcium carbonate shells, whose species composition and isotopic chemistry reflect past ocean temperatures and chemistry. And there are layers of volcanic ash, sometimes called tephra layers, derived from eruptions of Andean volcanoes. Those ash layers are particularly useful. When a large Andean volcano erupts, it can deposit a distinctive layer of ash across a wide area of the adjacent ocean floor. Because many of these eruptions can be dated independently through radiometric methods, through ice core records, through historical documentation of more recent events, ash layers in sediment cores serve as time markers, anchoring the sediment record in absolute time. A researcher who finds an ash layer from a known eruption can say with confidence that the sediment above it is younger than that event, and the sediment below it is older. This allows the entire record to be calibrated, turning a column of mud into a dated archive. The combination of these records, organic carbon variations, foraminiferal assemblages, oxygen indicators, and dated ash layers, gives scientists a remarkably detailed picture of how conditions have changed in the southeastern Pacific over thousands to hundreds of thousands of years. Changes in El Niño frequency and intensity, shifts in the position or strength of the Humboldt current, periods of expanded or contracted oxygen minimum zones, the timing and magnitude of Andean volcanic episodes. All of these leave their traces in the sediment, and patient analysis can extract them. What makes this particularly valuable is the length of the record that is, in principle, available. The Peru Chile Trench has been accumulating sediment for a very long time. In some areas, sediment thickness on the trench floor runs to hundreds of meters, representing millions of years of deposition. Not all of that is easily accessible. The deepest and oldest layers are compressed, altered, and difficult to core. But even the upper portions of the sediment column, accessible with standard coring equipment, can capture records extending back tens of thousands of years. That is long enough to span multiple glacial cycles, multiple periods of dramatically different climate, and many thousands of El Niño events. For climate scientists, this kind of long baseline is genuinely difficult to overstate in its value. Instrumental records of ocean conditions go back, at best, a century and a half, and even those early records are sparse and geographically uneven. Paleoclimate records from sediment cores extend the picture backward by orders of magnitude, allowing researchers to see how the El Niño system behaved during the last ice age, during the warm periods between ice ages, and during the abrupt climate transitions that punctuate the Pleistocene. Understanding how El Niño varied under different background climate states is directly relevant to projecting how it might behave as the planet warms, and the Peru Chile Trench sediments are one of the best places on Earth to look for that information. There is something quietly remarkable about this. The same trench that generates some of the most violent earthquakes on the planet, that has sent tsunamis across the Pacific, that harbours strange life under crushing pressure, is also functioning as a meticulous archive. Every year, a thin layer of sediment settles onto its floor, recording the state of the ocean above, the productivity of the current, the chemistry of the water, the occasional violence of a distant volcanic eruption. Layer by layer, year by year, it builds a record that human observers could never have assembled directly, because the record extends far beyond the span of any human civilization. It is a little like discovering that the most geologically dangerous place in the region is also its most careful historian. The trench does not choose to record these things, of course. It simply is what it is, a deep basin where sediment accumulates and is preserved, where the conditions happen to be right for keeping organic material and microscopic fossils intact over long periods. But the effect is the same as if someone had been keeping notes. Researchers who work with these sediment cores often describe the experience of reading them as genuinely absorbing, not in a dramatic way, but in the way that any detailed, patient record becomes absorbing when you understand what it is telling you. A shift in the ratio of certain foraminiferal species is not exciting in isolation, but when you know that shift reflects a change in sea surface temperature 300 meters above the trench floor 8,000 years ago, during a period when the climate was transitioning out of a glacial maximum, it becomes something else. It becomes a data point in a much larger story about how the planet regulates itself. The trench also interacts with the carbon cycle through the chemistry of its bottom water. At Hadal depths, microbial communities in the sediment are actively processing organic material, breaking it down, consuming oxygen, producing carbon dioxide and methane. The chemistry of the water just above the sediment surface is measurably different from the chemistry of the overlying water column, reflecting this microbial activity. In organic-rich trenches like the Peru Chile Trench, the oxygen demand from microbial decomposition can be significant, contributing to the expansion of low oxygen zones in the water column above. These oxygen minimum zones, which are already pronounced in the Eastern Pacific due to the high productivity of the Humboldt Current, have consequences for marine life throughout the water column, not just at the bottom. How these deep-sea chemical processes interact with broader ocean chemistry, and how they might respond to changes in surface productivity or ocean circulation driven by climate change, are questions that researchers are still working to characterize. The trench is deep enough and remote enough that continuous monitoring is extremely difficult, which means that the data available is patchy and the models are correspondingly uncertain. But the questions are real, and the answers matter, not just for understanding the trench itself, but for understanding how the ocean as a whole processes and stores carbon. All of this, the subduction of carbon into the mantle, the burial of organic material in trench sediments, the paleoclimate archive in the sediment cores, the deep water chemistry, points toward the same conclusion that keeps emerging from different directions when you study the Peru Chile Trench. This is not a place that exists in isolation. It is woven into the planetary system at multiple levels, from the geological to the biological, to the chemical to the climatic. What happens in the trench does not stay in the trench, and what happens in the world above, in the atmosphere, in the ocean currents, in the climate system, eventually finds its way down to the trench as well. That planetary connectedness is, in the end, what makes the trench so interesting to so many different kinds of scientists. A seismologist studying the plate interface, a biologist sampling amphipods from the trench floor, a paleoclimatologist reading sediment cores, a volcanologist tracking carbon emissions from Andean eruptions. They are all, in different ways, studying the same system. The trench is the point where the system is most visible, most concentrated, most legible, and yet it remains, for all the attention it has received, largely unread. The sediment archive is vast and mostly unsampled. The biology is documented in fragments. The carbon fluxes are estimated with wide uncertainties. The deep chemistry is monitored at only a handful of points, which brings the story naturally to where it has been heading all along, to the question of what it would take to actually understand this place, and what the future of that understanding might look like. So that is where things stand. A place that has been shaping this part of the world for tens of millions of years, and we have only been watching it carefully for a few decades. That gap between the scale of what the trench is and the scale of what we actually know about it is, honestly, one of the more humbling things you encounter when you spend time reading about it. The future of understanding the Peru-Chile Trench depends, more than anything else, on tools. Not theories. The theories are fairly well developed. Not curiosity. There is no shortage of that. What is missing is sustained, high-resolution observation of a place that is extraordinarily difficult to reach, extraordinarily expensive to study, and extraordinarily unforgiving of equipment failures. The trench does not cooperate. It sits at depths where pressure destroys conventional electronics, where temperatures hover near freezing year-round, where the nearest port of any size is hundreds of kilometers away, and where the weather in the southeastern Pacific can make surface operations difficult for weeks at a time. Doing science here is not like doing science in a laboratory or even on a research vessel in calm water. Every measurement is a small victory against the environment. What gives researchers genuine cause for optimism, though, is that the technology is genuinely improving. Autonomous underwater vehicles, AUVs, have become dramatically more capable over the past 20 years. Earlier generations were limited in depth rating, battery endurance, and the sophistication of their sensor packages. Current systems can reach hadal depths, navigate without a tether, collect water samples and sediment cores, and return to the surface with their data intact. They are still expensive, still occasionally lost, and still limited in how long they can operate before needing to return to the surface ship. But the trajectory is clear. Each generation of vehicles is more capable than the last, and the cost of deploying them, while still significant, is falling relative to what crewed deep-sea operations would require. For a trench that has never had a crewed vehicle reach its deepest point, AUVs represent the most realistic path to systematic exploration in the near term. Lander systems, those free-falling instrument packages that sink to the bottom under their own weight, collect data or samples, and then drop ballast to rise back to the surface, have also become more sophisticated. Early landers were relatively simple: a frame, some traps for catching organisms, a timer, a release mechanism. Modern landers carry acoustic modems for two-way communication, high-definition cameras, sediment corers, water samplers, and sometimes smaller instruments that can be deployed from the lander itself. Researchers have used lander systems extensively in the Peru-Chile Trench to collect the amphipods and other organisms that have revealed so much about the trench's biology and contamination levels. The advantage of landers is that they are relatively low cost compared to ROV or AUV operations, and they can be deployed from a wide range of vessels. The disadvantage is that they are passive. They go where you drop them, and they collect what comes to them. They cannot follow an interesting feature along the trench wall, or adjust their position in response to what they're seeing. For that, you need something that can move and think. The most transformative development on the horizon for trench science is probably seafloor sensor networks, arrays of instruments permanently deployed on the ocean floor, connected to each other and to the surface by fibre optic cables. These systems already exist in some parts of the world. The Ocean Networks Canada Cabled Observatory, for example, has been operating instruments on the seafloor off the coast of British Columbia since 2009, providing continuous real-time data on seismic activity, water chemistry, temperature and biological activity. The Japanese DONET network monitors the Nankai Trough subduction zone with a dense array of seismometers and pressure sensors on the seafloor, providing early warning capability and continuous scientific data. Nothing comparable exists along the Peru-Chile Trench, which is a significant gap given that this is one of the most seismically active subduction zones on the planet. A cabled seafloor observatory along even a portion of the Peru-Chile subduction zone would transform earthquake science in the region, providing the kind of continuous, high-resolution seismic data that is needed to understand how stress accumulates and releases along the plate interface, where slow slip events are occurring, and how the locked and unlocked segments of the fault are distributed. It would also provide early warning capability that could give coastal populations more time to respond to a major rupture. The technical and financial challenges of installing such a network in the deep, remote southeastern Pacific are considerable. But the scientific and humanitarian case for it is strong, and the technology to do it exists. What all of this points toward is a future in which the Peru-Chile Trench is no longer studied in fragments, a biological sample here, a seismic measurement there, a sediment core from one location, a bathymetric survey of another, but as a continuous, integrated system. That kind of comprehensive picture does not exist yet. The data available today is scattered across different institutions, different research programs, different national scientific agencies, collected at different times with different methods. Assembling it into a coherent understanding of how the trench works as a whole requires not just more data but better coordination between the researchers who collect it. There are international collaborations working on exactly this, and the scientific community studying subduction zones has become increasingly aware that the Peru-Chile system deserves more sustained attention than it has historically received. Partly this is because the Mariana Trench, as the deepest point on Earth, has attracted a disproportionate share of deep-sea exploration interest. The Peru-Chile Trench is not the deepest, but in terms of its scientific complexity, its hazard implications and its connections to surface systems, it may be the more consequential place to study. And through all of this, the sensor networks and the AUVs and the sediment cores and the seismic gaps, it is worth stepping back for a moment and simply sitting with what this place actually is, not as a scientific problem to be solved, but as a feature of the planet. A gash in the seafloor nearly 6,000 kilometers long, running parallel to one of the most dramatic coastlines on Earth. On one side, the Andes rise to nearly 7,000 meters above sea level. On the other side, the trench descends to more than 8,000 meters below sea level. The total relief, from the highest adjacent peaks to the deepest measured point, is somewhere around 15,000 meters, or roughly 15 kilometers of vertical distance, compressed into a relatively narrow horizontal span. There is nowhere else on Earth where the planet's surface varies so dramatically over such a short distance. The trench is not just deep. It is part of a landscape of extremes that has no real parallel. More than 10 million people live in Lima, just inland from the coast, within reach of the next major rupture of the plate interface that created this landscape. Millions more live in coastal cities from southern Peru through the length of Chile: Iquique, Antofagasta, Valparaíso, Concepción. These are not small towns. They are major urban centres, with ports and industries and histories that stretch back centuries, built on coastlines that have been reshaped by tsunamis more than once. The relationship between these populations in the trench is not abstract. It is the most direct possible relationship between human beings and a geological feature. The ground they live on and the sea they live beside are both products of the same process that has been running since before the Andes existed. The mountains behind them and the trench in front of them are the same story, told in different directions. That story is still being written. The Nazca Plate is still moving eastward at roughly 7 to 8 centimeters per year. The locked sections of the plate interface are still accumulating stress. The sediment is still settling onto the trench floor layer by layer, recording everything. The amphipods are still scavenging in the darkness, carrying in their tissues the chemical signature of a surface world they will never see. The volcanic arc is still active. Villarrica erupted as recently as 2015. El Misti sits above Arequipa with a population of nearly 1 million people in its shadow. The Humboldt Current is still sweeping northward along the coast, still driving the upwelling that makes these waters so productive, still responding to the El Niño cycles that periodically disrupt everything. None of this has stopped. None of it is waiting for us to finish studying it. There is something both unsettling and quietly wonderful about that. The trench does not require our attention to function. It was doing all of this long before anyone was watching, and it will continue long after the current generation of researchers has moved on. The earthquakes will come whether or not the seismic gaps are fully characterized. The sediment will accumulate whether or not anyone reads the cores. The organisms on the trench floor will evolve and adapt and die in the darkness whether or not we know their names. The planet is not pausing for us to catch up. It is simply proceeding at its own pace, on its own timescale, according to processes that began long before our species existed and will continue long after. What science offers in the face of all that is not control, it is understanding. And understanding matters, practically, because it shapes how coastal communities prepare for earthquakes and tsunamis, how early warning systems are designed, how land use decisions are made near fault zones, how fisheries are managed in the context of El Niño variability. But also in a quieter way, because there is something genuinely valuable about knowing where you are, about understanding that the ground beneath a city is not inert but active, that the ocean in front of a coastline is not a backdrop but a dynamic system connected to processes that reach all the way to the mantle. That knowledge changes how a place feels, even if it does not change what the place does. The Peru-Chile Trench is not a comfortable subject. It is a reminder that the planet is large, active, and indifferent to human timescales. The hazards it represents are real, and the gaps in our understanding of those hazards are real as well. But it is also a place of extraordinary richness, scientifically, biologically, historically, geologically. A place where the planet's interior and the planet's surface are in direct ongoing conversation, where the deepest ocean and the highest mountains are expressions of the same force, where life has found a way to exist under conditions that seem designed to prevent it, where the sediment on the floor holds a record of climate and ocean history that no human archive can match, where some of the largest earthquakes ever recorded were generated, and where the next ones are already being prepared, slowly in the dark. If you have stayed with this story all the way to this point, thank you, genuinely. These are not easy subjects to sit with. The scale is large, the uncertainties are real, and the implications for millions of people are serious. But they are important, and they are fascinating, and they deserve the kind of patient attention that this kind of narration tries to offer. I hope something here stayed with you. Maybe it was the image of the amphipods carrying industrial pollutants in their bodies at 8,000 meters of depth. Maybe it was the thought of lemur sitting above a plate interface that has not broken in nearly 300 years. Maybe it was the idea of sediment cores as a kind of geological diary, recording events that no one was alive to witness. Whatever it was, I'm glad you were here for it. If you found this worthwhile, a like or a subscribe means more than you might think. It helps this channel reach other people who are looking for exactly this kind of quiet, careful exploration. And if something in tonight's story surprised you, or raised a question you want to think about more, I would genuinely love to hear it in the comments. This is the kind of subject where the questions are often more interesting than the answers, and the conversation tends to go in directions I never anticipate. For now, the trench is still there, dark, deep, patient, and alive in its own geological way. The ocean above it is moving. The plates beneath it are grinding slowly toward whatever comes next. And somewhere on the seafloor in the permanent cold and darkness, a thin layer of sediment is settling, recording this particular moment in the long history of a restless planet. Sleep well.